Hello there, and welcome to Science for Sleep, where curiosity slows down, thoughts loosen their grip, and the universe is allowed to explain itself at a gentle pace. This is a place where questions are not rushed toward answers, where science is not a performance but a quiet companion, and where learning is something you can do with your eyes half closed and your shoulders finely relaxed. Tonight, you're invited to settle in, breathe a little more slowly, and let the world spin on without asking anything of you for a while. Because tonight's quiet exploration is about something that is always happening, whether we notice it or not. Something so steady, so reliable, that we almost never think to question it. The slow, constant turning of the earth beneath our feet. The motion that gives us sunrise and sunset, morning and night. The rhythm that quietly structures every day of our lives. Except, recently, something curious has been happening. The Earth, it seems, has been spinning just a little bit faster. Not fast enough to feel, not fast enough to notice by watching the sky or glancing at a clock on the wall, but fast enough that our most precise instruments, the kinds that can measure time down to fractions of a millisecond, have begun to raise an eyebrow. Days have become ever so slightly shorter. So slightly, in fact, that without atomic clocks and careful records, we might never have known at all. Still, the idea alone is enough to make the mind pause. A planet speeding up is not the kind of thing we expect. After all, we are taught that the Earth's rotation has been gradually slowing down for billions of years, stretched gently by the moon's pull, eased into longer days by tidal friction. That story has been remarkably consistent. Until now. So what does it mean when the planet decides, quietly and without announcement, to turn just a little faster? Is this a temporary wobble, a subtle adjustment, or a clue that something deep within Earth's systems is shifting in ways we are only beginning to understand? Before we begin to untangle that question, take a moment to notice where you are. Are you listening from a quiet room, a moving car, a darkened bedroom, or a place where the day is just winding down? And what time is it where you are right now? Not just the number on a clock, but the feeling of it. Late evening, early morning, somewhere in between. It's interesting, isn't it, that a conversation about Earth's rotation always meets us at a very specific moment in our own. If this kind of gentle wandering through science feels calming to you, if it helps your thoughts soften or your breathing slow, you're welcome to like the video or subscribe. It helps this small, quiet corner reach others who might need a slower pace tonight as well. And now, without rushing, let's ease into the story. Earth has been spinning for a very long time. Long before clocks existed, long before calendars, long before humans were here to name days or divide hours into neat countable pieces. The rotation of the planet is one of the oldest motions we know, set in place during Earth's formation more than 4.5 billion years ago, when swirling clouds of gas and dust collapsed into a young, molten world. That spin never stopped. It carried oceans, continents, storms, forests, cities, and eventually us, through countless sunrises and sunsets. Every culture that has ever existed has lived inside that turning, even if they explained it differently. Some imagine the sky rotating above a stationary Earth. Others imagine the Earth itself in motion, but the rhythm remained the same, one full turn, one day, at least roughly, because even at its most reliable, Earth's rotation has never been perfectly constant. From the very beginning it has been shaped, nudged, slowed, and adjusted by forces both external and internal. The moon's gravity pulls on the oceans, raising tides that drag slightly against the planet's crust. Earth's interior shifts, flows, and settles. Ice sheets grow and melt. Winds move vast masses of air around the globe. Earthquakes rearrange weight in subtle but measurable ways. All of these influences add up. Over long stretches of time, they change how fast the planet turns. For most of recorded history, the overall trend has been clear. Earth has been slowing down. Ancient days were shorter. Hundreds of millions of years ago, a day lasted perhaps 22 hours, then 21, then gradually lengthened toward the 24-hour rhythm we know today. Fossilized coral growth rings, laid down daily and yearly, tell this story quietly but convincingly. And yet, in the early 21st century, something unexpected appeared in the data. Instead of days continuing to lengthen, they began to shorten. Not dramatically, not enough to notice in daily life, but enough that scientists responsible for keeping global time synchronized had to pay attention. Enough that the concept of a negative leap second, something once considered unnecessary, entered serious discussion. So what could possibly make an entire planet speed up? The answer, as we'll slowly uncover, is not a single cause. It is a layered story, one that involves physics, geology, oceans, atmosphere, and timekeeping itself. It is a story where tiny changes add up, where invisible motions matter, and where Earth behaves not like a rigid machine, but like a complex living system that constantly adjusts itself. To understand why Earth's rotation might speed up, we first need to understand what rotation really means for a planet like ours, not just as a simple spin, but as a balance of mass, motion, and momentum. We need to understand how we measure time so precisely that 1,000th of a second becomes meaningful. And we need to understand how even small shifts in Earth's interior or on its surface can change how the whole planet turns. For now, there's nothing you need to remember or keep track of. The planet will keep turning, whether you're paying attention or drifting closer to sleep. And as we move forward, we'll take each idea gently, one at a time, allowing the story to continue without any rush at all. Beneath everything you have ever done, every conversation, every meal, every quiet moment before sleep, the ground has been moving. Not in a dramatic or unsettling way, not like an earthquake or a sudden shift, but in a steady, predictable motion that has never once paused since long before life began. The Earth rotates. It turns around an invisible line that runs from the North Pole to the South Pole. One full rotation takes about 24 hours, and that simple motion is responsible for one of the most familiar experiences we have, the passing of day into night. It sounds straightforward when we say it that way. A planet spins. But if we slow down and look more carefully, the idea becomes richer and more interesting than it first appears. When we talk about rotation, we are describing motion around an axis. Imagine placing a pencil straight through the center of a globe from top to bottom. Now imagine the globe spinning around that pencil. That pencil is the axis. For Earth, the axis is not a physical rod, of course. It is an imaginary line, tilted slightly at about 23.5 degrees relative to its orbit around the Sun. That tilt gives us seasons. The spinning gives us days. Rotation is one of the most basic properties of planets. In fact, it is nearly impossible for a planet not to rotate. The reason goes back to how planets form. Billions of years ago, before Earth existed, there was a cloud of gas and dust orbiting a young sun. That cloud was not perfectly still. It was already moving, swirling slowly under the influence of gravity. As gravity pulled material inward and the cloud began to collapse, it spun faster. This is a consequence of something called conservation of angular momentum, which we will explore more deeply later, but for now you can think of it this way. When a spinning system shrinks, it spins faster. A simple example helps. If you have ever watched a figure skater pull their arms inward during a spin, you have seen this principle in action. When their arms are extended, they rotate more slowly. When they bring their arms close to their body, they spin faster. Nothing external is pushing them to speed up. It happens because their mass is distributed differently. The early Earth formed from material that was already rotating. As that material gathered into a more compact sphere, the rotation rate increased. From that moment forward, the planet has been spinning. So when we say that Earth rotates, we are describing a motion that began with its birth. At the equator, the surface of Earth is moving at roughly 1,670 kilometers per hour, relative to the axis. That sounds fast, and in absolute terms it is. But because everything around us, the air, the oceans, the ground, and our own bodies, is moving at exactly the same speed, we do not feel it. Motion only becomes noticeable when there's a difference in speed or direction relative to something nearby. Since we're all rotating together, it feels perfectly still. This shared motion is important. If Earth suddenly stopped rotating, the consequences would be catastrophic. The atmosphere would continue moving eastward at tremendous speed, oceans would surge, and the balance of day and night would collapse into something unrecognizable. Fortunately, no such abrupt change is happening. The variations scientists are measuring are subtle, measured in milliseconds. Still, to understand why those milliseconds matter, we need to understand what a rotating planet really is, physically speaking. Earth is not a rigid, perfectly solid ball. It has layers. The outermost layer, the crust, is thin compared to the whole planet. Beneath that lies the mantle, which is solid but behaves plastically over long time scales. Deeper still is the outer core, which is liquid, and at the very centre is the solid inner core. Each of these layers interacts with the others. They do not move completely independently, but they are not locked together as a single uniform block either. Rotation in such a layered body is more complex than rotation in a solid metal sphere. Small shifts in mass distribution inside the planet can subtly alter how it spins. Just as a skater's spin changes when their arms move, Earth's rotation can change when mass shifts from one place to another. This is where the concept of angular momentum becomes central. Angular momentum is the quantity that describes rotational motion. It depends on two things: how fast an object is rotating, and how its mass is distributed relative to the axis of rotation. The farther mass is from the axis, the greater its contribution to the overall angular momentum. In a simplified way, you can think of it like this. If more of Earth's mass is concentrated near the equator, it becomes harder to spin quickly. If mass shifts closer to the axis, toward the poles or deeper toward the centre, the planet can spin slightly faster. That might sound abstract, but we can see it happening on smaller scales. Consider a spinning office chair. If someone sits in it holding dumbbells at arm's length and then pulls the weights inward, their spin increases. They have not added energy. They have simply redistributed mass closer to the axis. Earth behaves in similar ways, though on a vastly larger scale. When ice melts and water redistributes across the oceans, when atmospheric patterns shift large volumes of air, when ocean currents move massive amounts of water, when the inner core subtly changes its rotation relative to the mantle, all of these processes slightly adjust the planet's mass distribution. And when that distribution changes, rotation can change too. It is also important to understand that rotation is not isolated from other motions. Earth is not just spinning, it is also orbiting the Sun. It is wobbling slightly on its axis in a motion called precession. The axis itself experiences small irregular motions known as nutation. None of these are dramatic in everyday life, but they are measurable. The planet is constantly in motion in multiple ways at once. Rotation is simply the most immediately relevant of these motions to daily human experience. It defines the length of a day. One full turn relative to the Sun gives us what we call a solar day. More precisely, Earth completes a rotation relative to distant stars in about 23 hours and 56 minutes. The extra 4 minutes come from the fact that Earth is moving along its orbit around the Sun at the same time it is rotating. This distinction matters in precise astronomy and timekeeping. There is a sidereal day, measured relative to distant stars, and a solar day, measured relative to the Sun. For everyday life, we use the solar day. But for understanding Earth's true rotation speed, scientists often rely on measurements relative to distant cosmic objects. You might wonder how we measure such a thing so precisely. After all, we cannot step outside the planet and watch it spin. Instead, scientists use a technique called very long baseline interferometry, which involves observing distant quasars, incredibly far away and stable cosmic radio sources. By tracking how Earth's rotation affects the apparent position of these objects, we can measure rotation with astonishing accuracy. Atomic clocks, meanwhile, provide an independent measure of time. They are so precise that they lose or gain less than a second over millions of years. By comparing the steady ticking of atomic time with the slightly irregular rotation of Earth, scientists can detect even tiny changes in the length of a day. This is how we know that some days in recent years have been slightly shorter than the standard 86,400 seconds. Not shorter by seconds, you would notice, shorter by milliseconds. Yet even that small shift is significant when it comes to global timekeeping systems. At this point, it is helpful to pause and reflect on something simple. Rotation is not just a number. It is not just a speed. It is a balance. A rotating planet is in constant negotiation with its own structure, its oceans, its atmosphere, and even the gravitational pull of its moon. The moon deserves special mention here. For billions of years, the moon has been slowing Earth's rotation through tidal friction. As Earth spins, the moon's gravity pulls on the oceans, creating tidal bulges. Because Earth rotates faster than the moon orbits, these bulges are dragged slightly ahead of the moon's position. The gravitational interaction between the bulges and the moon transfers angular momentum from Earth's rotation to the moon's orbit. The result is that Earth slows down very gradually and the moon moves farther away. This long-term slowing has been the dominant trend for much of geological history. That is why ancient days were shorter. Coral fossils and sediment layers record that hundreds of millions of years ago, there were more days in a year because each day was shorter. Given that background, the recent speeding up becomes more intriguing. It runs counter to the long-term trend. To understand how that is possible, we must recognize that multiple influences act on Earth's rotation at the same time. The moon's tidal braking is steady but slow. Other factors, such as internal mass redistribution or atmospheric circulation, can produce short-term fluctuations. These shorter-term variations can temporarily outweigh the long-term slowing. In other words, Earth's rotation is not a perfectly smooth curve trending in one direction. It is more like a gently descending line with small ripples superimposed on it. What we are observing now appears to be one of those ripples, though one large enough to attract attention. The key is that the planet is not a rigid object. It is dynamic. The oceans move, the atmosphere shifts, ice melts and accumulates. The inner core may rotate at a slightly different rate than the mantle. Each of these contributes, in small ways, to the overall rotational behaviour. It may help to think of Earth less like a spinning metal ball and more like a layered fluid-filled system in motion. The crust rides on a mantle that flows over millions of years. The outer core churns in liquid form, generating the magnetic field. The inner core sits at the centre, possibly oscillating slightly in its rotation relative to the layers above. When mass shifts within such a system, even subtly, the consequences can be detected in rotation. So when we ask what it means for a planet to rotate, we're really asking what it means for an entire complex system to maintain angular momentum while constantly redistributing mass internally and externally. It means that rotation is stable enough to give us predictable days and nights, yet flexible enough to respond to deep interior dynamics, surface processes, and gravitational interactions. It means that the length of a day is not fixed by some cosmic decree. It is the result of physics playing out continuously. Long before anyone could measure a millisecond, long before atomic clocks hummed quietly in temperature-controlled laboratories, human beings were already trying to answer a simple question: how long is a day? Not in the abstract sense, but in the practical sense. When should we wake? When should we plant? When should we gather, pray, trade, or rest? The length of a day was not just curiosity, it shaped survival. And yet, for most of history, we did not measure it with instruments, we measured it with shadows. If you imagine standing outside thousands of years ago, you would notice something dependable. The sun rises, climbs, reaches a highest point, then descends and disappears. The interval between one sunrise and the next becomes the natural unit of time. No equations needed, no calibration, just observation. Early civilizations relied on this visible rhythm. The ancient Egyptians placed tall obelisks upright in the ground and watched how their shadows moved. The length and direction of the shadow changed throughout the day. By marking these changes, they could divide daylight into segments. These were not hours as we know them. They varied with the seasons because daylight itself varies with the seasons. But they were consistent enough to organize life. Later, sundials became more refined. A carefully angled gnomon, the raised piece that casts a shadow, could track the sun's apparent motion more accurately. Still, these devices had limitations. They worked only in daylight. They depended on clear skies, and they measured solar time, which, as it turns out, is not perfectly uniform throughout the year. You may not have thought about this before, but the solar day is not exactly the same length every day. Earth's orbit around the Sun is slightly elliptical, and its axis is tilted. Because of these factors, the apparent motion of the Sun across the sky varies subtly throughout the year. The difference is small, amounting to seconds or fractions of minutes, but it is enough that solar noon does not occur at exactly the same clock time every day. For ancient observers, this was simply part of nature's variation. Precision beyond that was unnecessary. Water clocks emerged as one of the first attempts to measure time independent of sunlight. These devices, sometimes called clepsydrae, relied on the steady flow of water from one vessel to another. If the flow rate was controlled, time could be measured even at night. The Greeks, Chinese, and many other cultures refined these systems. Some added gears, floats, and indicators. These were significant advances. For the first time, time could be measured indoors and after dark. Yet even water is imperfect. Its flow rate changes with temperature, evaporation alters levels, precision was limited. Mechanical clocks marked a dramatic shift. By the late Middle Ages in Europe, large mechanical clocks appeared in towers. They used weights and escapements to regulate motion. The escapement mechanism allowed a controlled release of energy, producing the familiar ticking rhythm. These early clocks were not highly accurate by modern standards. They could drift by minutes or even hours per day. But they introduced something transformative: standardized time. Communities began to coordinate their activities based on clock time rather than the position of the sun. Hours became uniform segments. Timekeeping slowly detached itself from direct solar observation. The invention of the pendulum clock in the 17th century improved accuracy dramatically. Christian Huygens recognized that a pendulum's swing, under ideal conditions, has a consistent period. By incorporating pendulums into clock mechanisms, timekeeping precision improved to within seconds per day. That was revolutionary at the time, but even seconds were not enough for certain needs. Navigation demanded greater precision. Determining longitude at sea requires knowing the time difference between a ship's location and a reference point. John Harrison's marine chronometers in the 18th century allowed sailors to carry highly accurate clocks on voyages. These clocks resisted temperature changes and motion. For the first time, timekeeping accuracy became essential, not just for daily life but for global exploration. Despite these advances, all of these systems were still tied, directly or indirectly, to Earth's rotation. Clocks were calibrated to match the length of the solar day. The assumption was that Earth's rotation provided a stable standard. That assumption held for centuries. Then came the era of scientific instrumentation, and with it, a new way to think about time itself. In the early 20th century, quartz clocks emerged. Quartz crystals vibrate at a stable frequency when subjected to an electric current. These vibrations are remarkably consistent. Quartz clocks were far more accurate than mechanical clocks. They drifted by only fractions of a second per day. For most purposes, this was extraordinary precision. However, as technology advanced, particularly in telecommunications and astronomy, scientists began to notice something subtle. Even the most accurate quartz clocks, when compared carefully over long periods, reveal discrepancies that could not be explained by the clocks themselves. The Earth's rotation was not perfectly steady. Some days were slightly longer, some were slightly shorter. The changes were tiny, but they were real. To understand this, scientists needed something even more stable than quartz. They found it in atoms. Atomic clocks, first developed in the 1950s, rely on the natural oscillations of atoms, usually cesium. A cesium atom transitions between energy levels at an extremely consistent frequency. This frequency became the basis for redefining the second. Today, 1 second is defined as exactly 9,192,631,770 oscillations of radiation, corresponding to a specific transition in cesium-133 atoms. This definition does not depend on Earth's rotation. It does not depend on the Sun. It depends only on atomic properties. With atomic clocks, timekeeping reached a new level of precision. These clocks can measure time so accurately that they would lose or gain less than a second over millions of years. Once atomic time became available, scientists could compare it directly to Earth's rotational time, and that comparison revealed something fascinating. The length of a day, as defined by Earth's rotation, fluctuates. Over long timescales, it trends slower due to tidal friction from the Moon. But over shorter timescales, months to decades, it can vary due to changes in atmospheric circulation, ocean currents, seismic activity, and movements within Earth's core. The difference between atomic time and rotational time is tracked carefully. When the difference grows too large, adjustments are made. These adjustments are called leap seconds. A leap second is occasionally added to Coordinated Universal Time, or UTC, to keep atomic time aligned with Earth's rotation. Without these adjustments, civil time would slowly drift away from solar time. Noon would eventually occur at night, though it would take thousands of years to become obvious. Since the introduction of leap seconds in 1972, most adjustments have involved adding a second because Earth's rotation has generally been slowing. But recently, something unusual has happened. Some days have been slightly shorter than 86,400 atomic seconds. This is how we know the Earth has been spinning faster, even if only by fractions of a millisecond. Measuring this requires more than just atomic clocks. Scientists also use astronomical techniques, including very long baseline interferometry. This method involves observing distant quasars using multiple radio telescopes spread across the globe. By measuring the precise arrival times of radio signals at different locations, scientists can determine Earth's orientation and rotation with extraordinary accuracy. The combination of atomic clocks and astronomical observation allows us to detect changes in the length of a day down to microseconds. It is remarkable if you pause to consider it. We have reached a point where we can detect variations in planetary rotation that would have been unimaginable to earlier generations. The difference between the longest and shortest days in recent decades is only a few milliseconds. You would never notice it without instruments, and yet, those milliseconds matter. Global positioning systems depend on precise timing. Telecommunications networks rely on synchronized clocks. Financial markets timestamp transactions with high precision. Small discrepancies can accumulate into significant errors. This is why Earth's rotation speed is not just a curiosity. It is a measurable parameter that affects modern technology. Looking back, it is almost poetic in a quiet way, though not in the dramatic sense that we move from shadows on stone to oscillating atoms, from watching the sun's arc to listening to the hum of cesium. Each step brought us closer to understanding that time, as measured by Earth's rotation, is not perfectly constant. The day, it turns out, is not a fixed unit handed down unchanged since the planet formed. It is dynamic. When early civilizations measured the day, they were content with approximate regularity. When mechanical clocks were invented, people were amazed by minute level precision. Now we concern ourselves with milliseconds. This progression reflects not only technological advancement, but a shift in perspective. We no longer assume that natural cycles are perfectly steady. We measure them. We compare them. We track their variations. And as we continue exploring why Earth's rotation is speeding up, even slightly, it helps to remember that we would not even know about this change without centuries of innovation in timekeeping. The story of measuring the length of a day is a story of increasing precision. It is also a story of humility. Each time we improved our clocks, we discovered that nature was more subtle than we thought. For most of Earth's long life, its rotation has been doing something very unremarkable. It has been slowing down, not abruptly, not dramatically, just patiently, steadily, over immense spans of time that stretch far beyond human memory or recorded history. This slowing is so gentle that for thousands of years it went completely unnoticed. Even now, without modern instruments and careful analysis, it would remain invisible. Yet this quiet deceleration has shaped the length of our days, the rhythm of life, and the way time itself has unfolded on this planet. To understand why the recent speeding up of Earth's rotation stands out, it helps to first appreciate just how consistent the slowing has been, and how deeply rooted its cause is in the relationship between Earth and its nearest companion. The story begins with the Moon. The Moon did not always hang quietly in our sky at its current distance. Shortly after Earth formed, a colossal collision likely occurred between the young Earth and a Mars-sized body. From the debris of that impact, the Moon coalesced. At first, it orbited much closer than it does today. Earth, still hot and partly molten, was spinning much faster than it does now. From the moment the Moon settled into orbit, gravity linked the two bodies in a subtle but powerful exchange. Gravity does not pull evenly across an object. The side of Earth closest to the Moon feels a slightly stronger gravitational pull than the far side. This difference creates tidal forces. The most visible result is the rise and fall of ocean tides, but tides affect more than just water. The solid Earth itself flexes slightly under this pull. As Earth rotates, these tidal bulges are carried a little ahead of the Moon's position. They are not perfectly aligned with the line connecting Earth and Moon because Earth spins faster than the Moon orbits. This offset matters. The Moon's gravity pulls back on these bulges. That pull creates a torque, a twisting force, that acts against Earth's rotation. In response, Earth loses a tiny amount of its rotational energy. At the same time, that energy is transferred to the Moon, causing the Moon to move into a slightly higher orbit. The result is a slow exchange. Earth's rotation slows. The Moon drifts farther away. This process is known as tidal braking, and it has been operating for billions of years. We can measure the Moon's recession today. Laser ranging experiments which bounce laser beams off reflectors left on the Moon by Apollo astronauts show that the Moon is moving away from Earth at about 3.8 centimeters per year. That may not sound like much, but over geological timescales it adds up. As the Moon recedes, Earth's rotation continues to slow, lengthening the day. Evidence of this process is recorded not only in physics equations, but in rocks. Certain ancient organisms, such as corals and shellfish, grew in daily and seasonal patterns. Their skeletons contain growth rings, much like trees do. By examining fossilized specimens hundreds of millions of years old, scientists can count daily growth layers within annual cycles. This reveals how many days were in a year at different points in Earth's history. What they found was striking. Hundreds of millions of years ago, there were more days in a year. Not because the year was longer, but because each day was shorter. Around 400 million years ago, during the Devonian period, a day lasted about 21.8 hours. Go back even further, and days were shorter still. This aligns perfectly with the theory of tidal braking. As Earth slowly loses rotational energy, days grow longer. The process is gradual but relentless. For most of Earth's history, this slowing dominated everything else, but it did not happen in isolation. Earth has never been a perfectly uniform sphere. Its interior has evolved. Continents have formed and drifted. Ice ages have come and gone. Oceans have opened and closed. All of these processes redistribute mass across the planet, and as we have already explored, changes in mass distribution affect rotation. Over very long timescales, however, these effects tend to average out. The dominant trend remains the Moon's braking influence. This is why, for centuries, scientists assumed Earth's rotation was slowing in a fairly smooth, predictable way. Variations existed, but they were treated as minor fluctuations around a clear downward trend. Then measurements became precise enough to show that the story was more complicated. In the 19th century, astronomers began noticing discrepancies between predicted and observed positions of the Moon and planets. These discrepancies were small, but persistent. At first, they were attributed to imperfections in models or observations. Over time, it became clear that part of the issue lay in Earth's rotation itself. Earth does not slow down at a perfectly constant rate. It wobbles, speeds up slightly, slows down slightly, then continues its long-term deceleration. To understand why, we have to look inward. Earth's mantle flows slowly over millions of years. Its outer core circulates in complex patterns, driven by heat escaping from the interior. The inner core may rotate at a slightly different rate than the mantle. These internal motions affect how mass is distributed relative to Earth's axis. When mass shifts closer to the axis, rotation speeds up slightly. When mass shifts farther away, rotation slows. Ice ages provide a clear example. During glacial periods, vast ice sheets accumulate near the poles. This concentrates mass closer to the axis of rotation, allowing Earth to spin a bit faster. When those ice sheets melt, water spreads toward the equator, increasing Earth's moment of inertia and slowing rotation slightly. These changes are small but measurable. Atmospheric circulation also plays a role. Winds move enormous masses of air around the planet. Seasonal changes alter wind patterns. When atmospheric angular momentum changes, Earth's rotation adjusts to conserve total angular momentum. The oceans too are constantly in motion. Currents transport water across latitudes and depths. Large-scale phenomena like El Niño redistribute heat and mass, subtly affecting rotation. Earthquakes can even cause measurable changes. When a large earthquake rearranges mass within Earth's crust or upper mantle, it can alter the length of the day by microseconds. All of these effects create short-term variability. Still, for most of recorded history, these fluctuations occurred against the backdrop of an overall slowing trend. Days became longer by about 1.7 milliseconds per century on average. That number may seem trivial, but over millions of years it adds up. Without tidal braking, Earth would still be spinning far faster than it does today. Days might last only a few hours. Life as we know it would be very different. So for a long time, the narrative was clear. Earth slows, the Moon recedes, days lengthen. Then, in the latter part of the 20th century and into the early 21st, careful measurements began to show something unexpected. Some days were shorter than average. Some years showed a slight increase in rotation speed rather than a decrease. At first, these variations were treated as temporary noise, short-term fluctuations caused by atmosphere, oceans, or internal dynamics. But as records accumulated, it became apparent that something persistent might be happening. The shortest days ever measured began appearing in recent years, not dramatically shorter, but consistently so. This does not mean tidal braking has stopped. The Moon is still pulling, Earth is still losing rotational energy overall. But it does suggest that other factors are currently acting in the opposite direction, strongly enough to partially counter that long-term slowing. To appreciate how subtle this balance is, consider this. The total rotational energy of Earth is enormous. Changing it measurably requires the movement of vast amounts of mass or sustained forces over long periods. The fact that small shifts in atmosphere, oceans, or the deep interior can be detected at all speaks to the sensitivity of modern measurements. It also highlights something important about Earth as a system. The planet is not static. It is not a rigid clockwork mechanism winding down smoothly. It is dynamic, layered, responsive. Long-term trends coexist with short-term variations. Slow geological processes interact with fast atmospheric ones. The quiet history of Earth's slowing spin is not a simple straight line. It is a gentle curve with ripples, shaped by gravity, internal structure, and surface processes. Understanding that history gives context to what we are seeing now. The recent speeding up is not a contradiction of physics. It is a reminder that multiple influences act at once. Earth continues to turn just as it always has. The difference lies not in the motion itself, but in our ability to notice the smallest variations, and in what those variations may be telling us about the planet beneath our feet. If Earth were alone in space, spinning without any nearby companions, its rotation would be far simpler. It would still change over time, but slowly, guided mostly by what happens inside the planet itself. But Earth is not alone. It has a constant partner moving alongside it, one that has been shaping its rotation quietly and continuously for billions of years. The Moon. It does not push. It does not pull in any dramatic way that you could feel by standing outside at night. Its influence is subtle, patient, and persistent. And yet, over deep time, it has altered the length of Earth's days, stretched them, slowed them, and left a clear signature in stone, water, and motion. To understand how the Moon affects Earth's rotation, we need to talk about tides. Not just the rise and fall of ocean water along coastlines, but the physical interaction between gravity, motion, and friction that plays out across the entire planet. The Moon's gravity pulls on Earth. That pull is stronger on the side of Earth closest to the Moon, and weaker on the far side. This difference creates tidal forces. The oceans respond most visibly because water can move freely. Two tidal bulges form, one facing the Moon and one on the opposite side. If Earth did not rotate, these bulges would stay lined up with the Moon. But Earth does rotate, and it does so faster than the Moon orbits. Because of this, the tidal bulges are carried slightly ahead of the Moon's position. That small misalignment is everything. As the Moon pulls back on those forward-shifted bulges, it creates a torque, a twisting force. This force acts against Earth's rotation. In effect, Earth is trying to drag the tides ahead, and the Moon is gently resisting that motion. The result is friction. Not friction like sandpaper against wood, but gravitational friction. Energy is dissipated. Earth loses a tiny amount of rotational energy. That energy does not disappear. It is transferred to the Moon, increasing the Moon's orbital energy and causing it to move farther away. This exchange is slow, steady, and relentless. Every year the Moon drifts a few centimeters farther from Earth. Every century Earth's rotation slows by a fraction of a millisecond. Every million years the day lengthens just a little more. This process is so gradual that no single generation notices it. Even many civilizations rising and falling would see no meaningful change. Yet over billions of years the effect is profound. Early in Earth's history, days were much shorter. The planet was spinning rapidly after its formation. The Moon was closer, exerting stronger tidal forces. The braking effect was more intense. Over time, as the Moon moved outward, tidal forces weakened and the rate of slowing decreased. This is why the slowing of Earth's rotation is not constant. It has been faster in the past and is slower now. The further the Moon gets, the less leverage it has. Still, even at its current distance, the Moon continues to tug. Tides do not only affect the oceans, the solid Earth flexes as well. The crust rises and falls slightly under tidal forces, a phenomenon known as Earth tides. These movements are small, measured in centimeters, but they occur across the entire planet. This deformation contributes to energy loss. Rock is not perfectly elastic. When it flexes, some energy is dissipated as heat. This adds to the braking effect. So when we talk about tidal friction, we are talking about a combination of ocean movement, seafloor interaction, and solid Earth deformation. Water sloshes against coastlines and continental shelves. Currents flow. Friction with the seafloor converts kinetic energy into heat. The planet itself flexes and relaxes. All of this adds up. One way to appreciate the scale of this process is to consider what would happen if the moon suddenly vanished. Tides would diminish drastically. Earth's rotation would stop slowing at its current rate. Days would still change over time due to internal processes, but the dominant braking force would be gone. That tells us how important the moon has been. The moon's influence also explains why Earth and moon are gradually becoming tidally locked with respect to each other. The moon already shows the same face to Earth because its rotation period matches its orbital period. Earth is not tidally locked yet, but over extremely long timescales, if nothing else intervened, the system would evolve toward a state where Earth's rotation period matched the moon's orbital period. In that distant future, one day on Earth would last as long as a lunar month. That future lies billions of years away, and the sun's evolution will likely intervene long before then. Still, it illustrates the direction of the process. The key point is that tidal friction has a clear direction. It slows Earth's rotation. It always has. It always will, as long as the moon remains in orbit. Which brings us to an important realization. The moon cannot be responsible for Earth's recent speeding up. Its effect is steady and well understood. It does not suddenly reverse. It does not fluctuate wildly. Any short-term changes in Earth's rotation must come from somewhere else. This is why scientists were surprised when they began seeing days that were slightly shorter than expected. The moon's tug did not change, the tides did not stop, yet the rotation increased slightly. To make sense of that, we need to consider timescales. The moon operates over millions to billions of years. Atmospheric changes operate over days to seasons. Ocean circulation shifts over months to years. Ice sheets grow and melt over centuries. Core mantle interactions occur over years to decades. All of these processes sit on top of the long-term tidal braking trend. They can add small accelerations or decelerations without altering the overall direction set by the moon. Think of it like walking down a gentle slope while stepping over small bumps and dips. The slope still goes downward, but your speed varies moment to moment. The moon defines the slope. Other processes define the bumps. Understanding this distinction is crucial. When we say Earth's rotation is speeding up, we are not saying the moon's influence has stopped or reversed. We are saying that other effects are currently strong enough to temporarily offset part of that slowing. This is why the recent changes are measured in milliseconds, not seconds or minutes. The moon's braking effect is powerful over long timescales, but it is gentle on human timescales. The moon's role also helps explain why Earth's rotation has been slowing since the beginning, rather than speeding up due to internal contraction or cooling. Without tidal friction, Earth might have retained a much faster spin. The presence of a large moon has made Earth's rotational history unique among the terrestrial planets. Mars, for example, has small moons that exert negligible tidal influence. Its rotation has changed far less over time. Mercury is tidally locked with the Sun due to strong solar tides. Venus rotates slowly and retrograde, likely due to early collisions and atmospheric effects. Earth sits in between. Its rotation has been shaped by a balance of forces, with the moon playing a central role. As precise timekeeping improved, scientists were able to model the moon's effect with increasing accuracy. By calculating tidal energy dissipation and orbital dynamics, they could predict how Earth's rotation should change over time. Those predictions matched geological evidence remarkably well, which made the recent deviations all the more interesting. When measured rotation deviates from predicted values based on tidal braking alone, it signals that something else is happening. Not something dramatic, not something dangerous, but something worth understanding. This brings us naturally to the present moment, to the years in which some of the shortest days ever recorded occurred. To the question of why, after billions of years of slowing, Earth appears to be turning just a little faster. The moon continues its gentle tug, unchanged. The tides continue to rise and fall. Friction continues to drain rotational energy. Yet, layered on top of that, other motions are shifting mass and momentum in subtle ways. The story of tides and friction gives us the baseline. It explains why slowing is the default. At first glance, the question almost sounds like a trick. After everything we know about Earth's long, patient slowing, after billions of years of the moon quietly pulling and stretching our days longer, the idea that the planet might suddenly decide to spin faster feels wrong. It feels like a rule being broken. And yet, when scientists began to look closely at the data, that is exactly what appeared to be happening. Not dramatically, not in a way that would tilt the sky or shorten your evening, but enough to show up clearly in the most precise measurements we have. To understand why this is possible, we need to shift how we think about Earth's rotation. It is tempting to imagine the planet as a single solid object, like a spinning bowling ball that can only slow down or speed up if something external pushes it. But Earth is not like that. It is layered, fluid in places, flexible in others, and constantly rearranging its mass. Earth's rotation speed is not controlled by a single factor. It is the result of many influences acting at the same time, some steady and predictable, others variable and complex. The moon provides a long-term braking force, but layered on top of that are processes that can temporarily nudge the planet in the opposite direction. So when we ask why Earth is spinning faster, the answer is not one cause. It is a combination of subtle shifts, all happening within a system that obeys a very strict rule of physics: conservation of angular momentum. Angular momentum, in simple terms, must be conserved unless an external torque acts on the system. For Earth, the moon provides an external torque that slowly removes angular momentum over long periods. But within the Earth system itself, angular momentum is constantly being redistributed between the solid planet, the oceans, and the atmosphere. When that redistribution changes, rotation speed can change too. One of the most important contributors is the movement of mass inside Earth. Earth is not static beneath the surface. The mantle flows slowly over geological timescales. The outer core is liquid and in constant motion. The inner core may rotate at a slightly different rate than the mantle and crust above it. These motions are driven by heat escaping from Earth's interior and by complex interactions between layers. If mass shifts closer to Earth's axis of rotation, the planet spins faster. If mass shifts farther away, it spins slower. This is the same principle that governs the spinning skater pulling in their arms. Scientists have long suspected that interactions between the core and mantle play a role in short-term variations in Earth's rotation. Changes in the flow of liquid iron in the outer core can alter how angular momentum is shared between the core and the rest of the planet. When the core transfers angular momentum to the mantle, Earth's surface rotation can speed up slightly. These effects are small, but they occur on timescales of years to decades, which aligns with the period over which recent changes have been observed. Then there is the atmosphere. The atmosphere may seem light compared to the solid Earth, but it is massive. Winds move enormous quantities of air around the globe every day. When large-scale wind patterns change, they carry angular momentum with them. When the atmosphere gains angular momentum, Earth's rotation slows slightly to compensate. When the atmosphere loses angular momentum, Earth speeds up slightly. This exchange happens constantly. Seasonal changes play a role. During certain times of year, atmospheric circulation patterns shift in ways that affect rotation. Large-scale phenomena like the El Niño Southern Oscillation can alter wind patterns across the Pacific, redistributing mass and momentum on a planetary scale. These atmospheric effects are well documented and can explain some of the short-term fluctuations in the length of a day. However, they do not fully account for the recent trend toward shorter days. Oceans add another layer. Water is heavy. The oceans contain an enormous amount of mass, and they are constantly in motion. Currents transport water across latitudes and depths. When water moves closer to the equator, it increases Earth's moment of inertia and slows rotation. When it moves toward the poles, it can have the opposite effect. Changes in ocean circulation, driven by temperature differences, wind stress, and melting ice, can subtly influence rotation speed, which brings us to ice. Over the past century, large amounts of ice have melted from glaciers and ice sheets, particularly in Greenland and Antarctica. When ice melts, water that was once locked near the poles flows into the oceans and spreads toward lower latitudes. At first glance, this might seem like it should slow Earth's rotation, because mass is moving farther from the axis. And indeed, over longer timescales, glacial melting has been associated with a slight slowing effect. However, the picture is more complicated. When ice melts, the solid Earth responds. The crust beneath former ice sheets slowly rebounds upward in a process called glacial isostatic adjustment. This rebound redistributes mass within the planet, shifting material closer to the axis of rotation. At the same time, the redistribution of water is not uniform. Ocean basins deform under the changing load. Sea level rise is not the same everywhere. Some regions experience greater changes than others. The combined effect of melting ice, crustal rebound, and ocean redistribution can, under certain conditions, contribute to a slight speeding up of rotation over short timescales. Earthquakes also play a role, though a smaller one. When a major earthquake occurs, it can rearrange mass within Earth's crust and upper mantle. This redistribution can slightly alter Earth's moment of inertia, leading to tiny changes in rotation speed. These changes are usually measured in microseconds, but they are detectable. Large earthquakes have been shown to shorten the length of the day by fractions of a microsecond. Individually, these events are minor. Collectively, over time, they contribute to the overall variability. What makes the current situation especially interesting is that several of these influences appear to be aligning in the same direction. Internal core-mantle interactions, atmospheric circulation patterns, ocean dynamics, and surface mass redistribution may all be contributing small accelerations at the same time. Each effect is tiny on its own. Together they are enough to produce a measurable shortening of the day. This does not mean Earth has entered a new permanent phase of speeding up. The long-term trend of slowing remains intact. The moon has not stopped pulling. Tidal friction continues. What we are observing is more like a temporary fluctuation superimposed on a long, steady decline. Still, the fact that the shortest days ever recorded have occurred in recent years is not a coincidence. It reflects the sensitivity of Earth's rotation to changes in its internal and surface dynamics. Another important factor is how we define and measure suddenly. In everyday language, suddenly implies something abrupt or dramatic. In geophysics, suddenly can mean a change observed over a few decades instead of millions of years. The recent speeding up has unfolded over years, not days. It is only sudden relative to geological timescales. From Earth's perspective, nothing unusual is happening. The planet is doing what it has always done, adjusting continuously to shifting conditions. From our perspective, equipped with atomic clocks and precise instruments, we are noticing details that were previously invisible. It is also worth noting that Earth's rotation has sped up slightly before. Historical records suggest that similar variations have occurred in the past. What is new is our ability to detect them with confidence and to analyze them in real time. Scientists continue to study this phenomenon because it offers a window into Earth's interior and its coupled systems. Changes in rotation provide indirect clues about processes we cannot observe directly, such as flow patterns in the core. The speeding up is not a warning sign. It does not mean days will continue to shrink indefinitely. It does not threaten life or stability. It is a reminder that Earth is dynamic, not static. The planet responds to changes in mass, energy, and motion in ways that obey physical laws but play out in complex combinations. For most of human history, no one would have noticed if a day was shorter by a millisecond. Even if it were shorter by 10 milliseconds, nothing in daily life would have revealed it. The sun would still rise. Shadows would still move. Clocks, until very recently, would not have been precise enough to show the difference. And yet, in the past few years, scientists have quietly recorded something remarkable. Several of the shortest days ever measured have occurred in the modern era, not shorter by minutes, not even by seconds, but by fractions of a millisecond compared to the standard 86,400 seconds that define a day in atomic time. To understand why that matters and why it has attracted attention, we need to look at how these records are identified in the first place. The length of day is not determined by a wall clock. It is calculated by comparing two independent time systems. One is atomic time, measured by atomic clocks that count the oscillations of cesium atoms with extraordinary stability. The other is Earth rotation time, determined by astronomical observations of the planet's orientation relative to distant cosmic objects. Atomic clocks define the international system of units second. They tick at a rate that does not depend on Earth's motion. Earth rotation time, on the other hand, reflects how long the planet actually takes to complete one rotation relative to the Sun. If Earth rotated perfectly steadily, these two systems would remain aligned. But because Earth's rotation fluctuates, they drift apart slightly. Scientists track this difference continuously. The difference between atomic time and Earth rotation time is expressed in terms of milliseconds added to or subtracted from the standard 86,400 seconds. For decades, the general trend showed that Earth was rotating slightly slower than her atomic time would suggest. Days were fractionally longer than 86,400 seconds. This is why leap seconds have been added occasionally since 1972 to keep coordinated universal time aligned with Earth's rotation. But in recent years, something shifted. Starting around 2020, Earth began setting records for the shortest days since precise measurements began. For example, in July 2020, one day was measured to be approximately 1.46 milliseconds, shorter than 86,400 seconds. That may sound insignificant, and in everyday life it is, but in the context of planetary rotation, it is notable. Then came additional records. In 2021 and 2022, even shorter days were observed. In June 2022, one day was recorded as being about 1.59 milliseconds shorter than the standard length. Each of these measurements represented the fastest rotation since modern tracking began. It is important to emphasize that these are not isolated anomalies caused by measurement errors. The instruments involved are extremely precise. Multiple independent systems confirm the results. So what makes these particular days shorter? The answer lies not in a single dramatic event, but in the accumulation of subtle influences. Earth's rotation speed is affected by how mass is distributed across the planet. When mass shifts closer to the axis of rotation, the planet spins faster. When mass moves outward, it spins slower. The shortest days tend to occur when several accelerating influences align. Atmospheric circulation plays a role. Certain wind patterns can transfer angular momentum in ways that cause the solid Earth to rotate slightly faster. When the atmosphere slows relative to the surface, Earth speeds up to conserve total angular momentum. Ocean currents also contribute. Shifts in large-scale circulation can move mass in ways that reduce the planet's moment of inertia slightly. There is also evidence that interactions between Earth's core and mantle may be involved. The liquid outer core does not rotate exactly in lockstep with the mantle and crust. Variations in core flow can exchange angular momentum with the outer layers, leading to subtle changes in surface rotation speed. These processes are complex and not fully understood. They are studied through a combination of satellite data, seismic observations, and mathematical modelling. One of the reasons the recent shortest days have drawn attention is that they appear in clusters rather than as isolated outliers. Several of the shortest days on record have occurred within a span of a few years. This suggests that the accelerating influences are not random noise, but part of a broader pattern. Still, the changes are small. To put it in perspective, a difference of 1.5 milliseconds in the length of a day accumulates slowly. It would take about 667 days of being 1.5 milliseconds shorter to shorten a full second. And even that full second would only matter in the context of precise timekeeping systems. For most human activities, these variations are invisible. However, for systems that rely on extremely precise timing, such as GPS satellites and telecommunications networks, even small discrepancies can matter. GPS satellites carry atomic clocks and account for relativistic effects due to their speed and altitude. They also account for Earth rotation variations to maintain accuracy. This is why discussions have begun about the possibility of a negative leap second. Until now, leap seconds have always been added because Earth was running slightly slow. If Earth continues to spin faster relative to atomic time, it could become necessary to subtract a second from coordinated universal time. That has never been done before. The very idea illustrates how closely our technological systems are tied to Earth's rotation, even as we define time using atomic standards. The mystery is not that Earth can spin slightly faster. Physics allows for that. The mystery lies in why the recent acceleration has been persistent enough to set records. Some researchers point to changes in atmospheric circulation patterns over the past few years. Others emphasize the role of core mantle interactions. Still others examine the effects of climate-driven mass redistribution, including melting ice and sea level rise. It is likely that no single factor explains the phenomenon. Instead, it appears to be a combination of influences acting together. Another point worth considering is natural variability. Earth's rotation has always fluctuated. Historical data from astronomical observations show that similar short-term accelerations have occurred in the past. What makes the current period distinctive is not necessarily the magnitude of the acceleration, but the precision with which it is measured and documented. In other words, part of the mystery is perceptual. We are seeing details now that were previously beyond our observational capabilities. Yet even with that perspective, the recent clustering of shortest days remains intriguing. Scientists continue to analyze patterns in length of day data to determine whether the current acceleration is temporary or part of a longer-term oscillation. Some models suggest that rotation speed varies in cycles of several decades, linked to processes deep within Earth's core. If so, the recent speeding up may be part of a natural oscillatory pattern rather than a permanent shift. What makes this topic especially interesting is that Earth's rotation is not just a surface phenomenon. It is a reflection of the entire planet's internal dynamics. Changes in rotation can provide indirect clues about processes that cannot be observed directly. The shortest days on record are not a threat. They do not signal instability or danger. They are a reminder that Earth is a living system in motion, responding to forces both internal and external. The fact that we can measure such tiny changes at all speaks to the extraordinary precision of modern science. Far below the continents, below the oceans, below the deepest mines and the longest drill holes humanity has ever managed to carve into the crust, the planet continues in a state we cannot directly see. The surface feels solid and dependable, but beneath it, Earth is layered, dynamic, and in constant motion. And somewhere within those hidden layers lies one of the most intriguing pieces of the rotation puzzle. If the length of a day changes, even slightly, something inside the planet may be involved. To understand how that is possible, we need to travel inward in a conceptual sense, layer by layer. The outermost layer of Earth is the crust, thin and brittle compared to everything below it. Beneath the crust lies the mantle, which makes up most of the planet's volume. Although the mantle is solid rock, it behaves plastically over long timescales, slowly flowing due to the immense heat rising from below. Deeper still lies the outer core, a vast ocean of liquid iron and nickel swirling under extreme temperatures and pressures. At the very centre sits the inner core, a solid sphere composed mostly of iron, compressed by gravity into a state that remains solid despite temperatures comparable to the surface of the Sun. These layers are not isolated. They interact through gravity, pressure, and electromagnetic forces. They exchange heat. They exchange momentum. When we talk about Earth's rotation, we often imagine the planet turning as a single rigid body. For most practical purposes, that approximation works. But in reality, the different layers can move relative to one another, even if only slightly. The outer core, in particular, is in constant motion. Convection currents move liquid metal around in complex patterns. These flows generate Earth's magnetic field through a process known as the geodynamo. That magnetic field shields the planet from solar radiation and helps preserve our atmosphere. But those flows do more than generate magnetism. They also carry angular momentum. Angular momentum is not confined to the surface. It exists in every rotating part of the planet. When fluid iron in the outer core changes its circulation pattern, it can exchange angular momentum with the mantle above it. If the core transfers angular momentum to the mantle, the surface of Earth can rotate slightly faster. If the mantle transfers angular momentum back to the core, surface rotation can slow. These exchanges are subtle. They do not produce noticeable changes in daily life, but with atomic clocks and astronomical measurements, they are detectable. One of the challenges scientists face is that we cannot directly observe the core. It is too deep. Instead, we rely on indirect methods, primarily seismic waves generated by earthquakes. When an earthquake occurs, it sends waves travelling through Earth. Some waves pass through the mantle, some pass through the core. By studying how these waves are refracted, reflected, and delayed, scientists can infer properties of the core, including its structure and motion. Over the past few decades, evidence has emerged that the inner core may rotate at a slightly different rate than the mantle and crust. This phenomenon is sometimes described as superrotation or differential rotation. The difference is tiny, measured in fractions of a degree per year, but even a small mismatch can influence the distribution of angular momentum within the planet. If the inner core speeds up relative to the mantle, it may temporarily slow the surface. If it slows relative to the mantle, the surface may speed up slightly. Recent studies suggest that the inner core's rotation may not be constant. It may oscillate over decades, speeding up and slowing down relative to the mantle in a cyclical pattern. If that is true, then part of the recent speeding up of Earth's rotation could be linked to where we are in that oscillation cycle. The outer core also plays a role. Its liquid flows are influenced by temperature gradients and by interactions with the magnetic field. Changes in core flow patterns can alter the distribution of mass and momentum within the planet. Because the core contains a significant fraction of Earth's mass, even small shifts in its motion can have measurable effects on rotation. There is also coupling between the core and mantle through electromagnetic forces. The magnetic field lines generated in the core interact with conductive materials in the lower mantle. This creates a form of magnetic coupling that can transfer angular momentum between layers. Imagine two spinning objects connected by a flexible but conductive link. Changes in one can influence the other. In Earth's case, that link is invisible and governed by physics we can describe mathematically, but cannot see directly. What makes this especially interesting is that variations in the magnetic field sometimes correlate with changes in rotation speed. When geomagnetic jerks, sudden changes in the rate of change of the magnetic field occur, they are sometimes accompanied by small changes in the length of day. This suggests that the processes driving magnetic field variations and those influencing rotation are connected. None of this implies instability. The core's movements are natural and ongoing. They have been occurring for billions of years. What has changed is our ability to detect their effects. Another factor to consider is the redistribution of mass within the mantle. Mantle convection drives plate tectonics. Continents move slowly over millions of years. Subduction zones recycle crust into the mantle. Mantle plumes rise toward the surface. While these processes are slow, they contribute to the long-term evolution of Earth's mass distribution. On shorter timescales, post-glacial rebound is particularly important. During the last ice age, massive ice sheets pressed down on parts of the crust. When those ice sheets melted, the crust began to rebound upward. That rebound is still ongoing in some regions today. As the crust rises and the mantle beneath it flows, mass is redistributed slightly closer to or farther from the axis of rotation. In some cases, this redistribution can reduce Earth's moment of inertia just enough to cause a tiny increase in rotation speed. All of these internal processes are layered on top of one another. Core oscillations, mantle flow, crustal rebound, magnetic coupling. Each contributes a small piece to the overall picture. When we observe that Earth has experienced some of the shortest days on record, it is tempting to search for a single cause. But the reality is more complex. The core's subtle movements likely play a role, but they do not act alone. They are part of a network of interactions extending from the centre of the planet to the top of the atmosphere. What makes the core especially compelling is that it operates on timescales that align with the recent changes. Decadal oscillations in core rotation could explain why the acceleration appears clustered in certain periods. Researchers continue to analyse seismic data and magnetic field measurements to refine their understanding. As models improve, the link between core dynamics and rotation variations becomes clearer. Still, there is uncertainty. The core is not directly observable. Our models are constrained by available data, but they remain approximations. That uncertainty is not a weakness. It is part of how science progresses. Each new measurement refines the picture. For now, the evidence suggests that the core's subtle movements are one of the contributors to Earth's recent slight acceleration. Not the sole cause, but a meaningful part of the explanation. From space, Earth looks calm and complete, a blue sphere with white swirls and brown land masses drifting slowly across its surface. From the ground, oceans often feel stable and constant, stretching to the horizon with a sense of permanence. But in reality, the oceans are never still. They're always moving, shifting, circulating, rising, sinking, and flowing in patterns that span the entire planet. And because water is heavy, unimaginably heavy when spread across global scales, those movements matter. They matter not just for weather, climate, and marine life, but for something even more fundamental. They matter for how fast Earth rotates. To understand why oceans play a role in Earth's rotation speed, it helps to revisit a simple idea that keeps appearing in this story. Rotation depends on how mass is distributed. When mass moves closer to the axis of rotation, spin increases. When mass moves farther away, spin decreases. The oceans contain roughly 1.4 billion cubic kilometers of water. That water is not evenly distributed. It piles up in some regions, thins out in others, and constantly shifts due to winds, temperature differences, salinity, Earth's rotation itself, and the shape of the seafloor. Every one of those movements redistributes mass. Unlike the solid Earth, which changes shape slowly, the oceans respond relatively quickly. Winds can push surface waters across entire basins. Temperature changes can alter density, causing water to sink or rise. Currents can transport vast amounts of water from equator to pole and back again. All of this happens continuously. At first glance, it might seem unlikely that ocean movement could influence something as massive as Earth's rotation. After all, the oceans make up only a small fraction of Earth's total mass. But what matters is not just how much mass moves, but where it moves. Water that shifts toward the equator increases Earth's moment of inertia, because it moves farther from the rotation axis. Water that shifts toward the poles decreases the moment of inertia, because it moves closer to the axis. Even small changes, when applied to such large volumes, can have measurable effects. One of the most important oceanic processes in this context is large-scale circulation. Ocean currents are not random. They follow organised patterns driven by wind, Earth's rotation, and differences in temperature and salinity. Warm water tends to move away from the equator toward higher latitudes. Cold water tends to sink and flow back toward the equator at depth. This global conveyor of water moves heat around the planet and plays a critical role in regulating climate. As water moves poleward or equatorward, it carries mass with it. When these circulation patterns strengthen or weaken, the distribution of mass across latitudes changes. Seasonal variations alone can produce detectable changes in Earth's rotation. During certain times of year, ocean circulation shifts slightly in response to changing winds and temperature gradients. These shifts are small, but they are synchronized across large regions. Then there are longer-term patterns. One of the most influential ocean-atmosphere interactions is the periodic warming and cooling of surface waters in the tropical Pacific. This phenomenon alters wind patterns, rainfall, and ocean circulation across much of the globe. When surface waters in the Pacific warm, the distribution of water mass changes. Sea level rises in some regions and falls in others. Currents adjust. These changes affect how mass is arranged relative to Earth's axis. Studies have shown that such events can influence the length of the day by fractions of a millisecond. Again, this is not something you would ever feel, but it is measurable. Another important factor is sea level change. Sea level does not rise uniformly. It varies regionally due to ocean currents, gravitational effects, and the shape of the ocean basins. When ice melts on land, the added water does not simply spread evenly across the oceans. As ice melts, two things happen simultaneously. Water is added to the oceans and the solid Earth responds to the removal of weight. Regions once pressed down by ice slowly rise. Regions farther away may sink slightly in response. This complex response changes the shape of Earth's surface and the distribution of the mass. In some cases, water redistribution associated with melting ice and ocean circulation can temporarily move mass closer to the axis of rotation, contributing to a slight increase in rotation speed. It is important to be clear here. Over very long timescales, melting ice tends to slow Earth's rotation because water spreads toward lower latitudes. But on shorter timescales, especially when combined with crustal rebound and ocean basin deformation, the net effect can be more nuanced. The oceans also interact directly with the solid Earth through friction. As tides move water back and forth across continental shelves, energy is dissipated. This tidal friction contributes to the long-term slowing of Earth's rotation, as we discussed earlier, but tides also redistribute water mass on daily and monthly cycles. The distribution of tidal bulges changes continuously as the Moon orbits Earth. These changes slightly alter Earth's moment of inertia throughout the day. On their own, these effects average out. But when combined with other oceanic and atmospheric changes, they contribute to the overall variability. Another factor to consider is the Coriolis effect. Because Earth rotates, moving water is deflected. This deflection shapes ocean currents and gyres. In turn, the structure of these currents influences where water mass accumulates. When large-scale circulation patterns shift, the Coriolis-driven balance changes as well. This alters the way momentum is distributed between the oceans and the solid Earth. Momentum exchange between oceans and Earth happens through friction at the seafloor and along coastlines. When currents accelerate or decelerate, angular momentum is transferred. If ocean circulation slows relative to Earth's surface, Earth can speed up slightly. If it accelerates, Earth can slow slightly. This exchange is continuous and dynamic. Satellite measurements have helped scientists track changes in ocean mass distribution with increasing precision. Satellite altimetry can measure sea level changes down to millimeters. Gravity sensing satellites can detect changes in mass distribution across Earth's surface. By combining these data with rotation measurements, scientists can link specific oceanic changes to observed variations in the length of the day. What emerges from these studies is not a single cause and effect relationship, but a web of interactions. Oceans respond to atmospheric forcing. The atmosphere responds to temperature gradients. Ice melt alters ocean mass. The solid Earth responds to changing loads. All of these processes feed back into rotation. The oceans are particularly important because they can respond relatively quickly. Atmospheric changes can shift winds in days or weeks. The oceans respond over months to years. Core processes respond over years to decades. Tidal breaking operates over millions of years. This layered timing means that ocean dynamics are well positioned to contribute to short-term variations like those seen in the shortest days on record. Another subtle but important point is that ocean mass redistribution does not need to be large to matter, because the effect depends on distance from the axis. Moving water a small distance across latitude lines can have a measurable impact. Imagine sliding a heavy weight a short distance toward or away from the centre of a spinning disk. The disk's rotation changes even though the weight itself has not changed. Earth is that disk. The oceans are the moving weight. This does not mean that oceans are the dominant driver of Earth's rotation changes. They are one contributor among several, but their role is significant enough that it cannot be ignored. In recent years, changes in ocean circulation and sea level patterns appear to have aligned with other accelerating influences, such as atmospheric changes and core mantle interactions. Together, these effects have contributed to the observed shortening of the day. What makes this especially interesting is that ocean dynamics are closely tied to climate variability. As climate patterns shift, ocean circulation adjusts. That adjustment affects mass distribution, which affects rotation. This does not mean climate change is directly causing Earth to spin faster in a simple way. The relationship is indirect and complex. But it does mean that changes at the surface of the planet can have consequences that reach all the way to the timing systems we use to define a day. The oceans remind us that Earth's rotation is not controlled solely by deep hidden processes. It is also influenced by the moving surface of the planet, by water flowing across basins and responding to winds and heat. When we think about ice melting, the first images that usually come to mind are glaciers retreating, polar bears navigating thinning sea ice, or sea levels slowly rising along coastlines. What does not immediately come to mind is the rotation of the entire planet changing by fractions of a millisecond. And yet, melting ice is one of the many processes that subtly shifts Earth's mass distribution, and therefore its spin. To understand how this works, it helps to picture Earth not as a rigid sphere, but as a rotating system whose speed depends on how weight is arranged relative to its axis. The axis of rotation runs from the North Pole to the South Pole. Mass located near that axis contributes less to Earth's moment of inertia than mass located near the equator. When weight moves outward, farther from the axis, rotation tends to slow slightly. When weight moves inward, close to the axis, rotation can speed up. Ice sheets store enormous amounts of mass near the poles. Greenland and Antarctica hold the majority of Earth's freshwater ice. When this ice melts, water flows into the oceans. At first glance, that seems straightforward. Mass moves from high latitudes toward lower latitudes, spreading across the seas. That outward redistribution should, in principle, increase Earth's moment of inertia and slow rotation. Over long timescales, that is indeed what happens. But as with most things in this story, the details are more complex. When massive ice sheets form, they press down on the crust beneath them. The weight of kilometers thick ice deforms the solid Earth, pushing the crust downward into the mantle. The mantle, though solid, behaves like a very slow-moving fluid over thousands of years. It flows away from the compressed region. When the ice melts, the pressure is removed. The crust begins to rebound upward in a process called glacial isostatic adjustment. The mantle slowly flows back toward the region that was previously compressed. This rebound redistributes mass within the planet. Rock that had been displaced outward begins to move back inward. The surface rises, but the deeper response involves shifts that alter how mass is arranged relative to the rotation axis. In some regions, this rebound effect can move mass slightly closer to the axis, contributing to a small increase in rotation speed. Meanwhile, the water from melted ice does not simply spread evenly across the oceans. The redistribution of water is shaped by gravity, Earth's rotation, and the structure of ocean basins. There is a subtle gravitational effect at work here. Large ice sheets exert their own gravitational pull on surrounding ocean water. When ice melts, that pull weakens. Water that had been attracted toward the ice sheet redistributes away from it. This leads to complex regional patterns of sea level change rather than a uniform global rise. The Earth's crust also deforms elastically and viscoelastically under changing loads. As mass shifts, the shape of the planet adjusts slightly. These shape changes alter Earth's moment of inertia. All of this means that the net rotational effect of melting ice is not as simple as mass moves outward, rotation slows. It depends on how the entire Earth system responds. On very long timescales, glacial cycles have clearly influenced rotation. During ice ages, when large volumes of ice accumulate near the poles, mass is concentrated closer to the axis, and rotation speeds up slightly. When ice melts, rotation slows. But the present era is not just about surface melting. It is about the ongoing adjustment from the last ice age as well. The last glacial maximum occurred about 20,000 years ago. Since then, ice sheets have retreated dramatically. The crust in regions like Canada and Scandinavia is still rising today as a result of that melting. This ongoing rebound continues to shift mass inside the planet. In some models, the rebound effect can outweigh the outward redistribution of water over certain timescales, leading to a small net acceleration of rotation. It is important to emphasize that these effects are tiny. We are talking about changes measured in milliseconds or microseconds. No one feels them. They do not alter sunrise times in any noticeable way. However, they are large enough to show up in high-precision rotation data. Another factor to consider is that melting ice is not the only surface mass change happening at the same time. Groundwater extraction, reservoir filling behind dams, and seasonal snow cover variations all redistribute mass. For example, when large reservoirs fill with water, mass is concentrated in specific regions. When groundwater is pumped from aquifers and eventually flows to the ocean, mass shifts toward lower latitudes. Individually, these human-driven changes are small compared to the mass of glaciers and oceans. Collectively, they contribute to the overall mass redistribution picture. Climate-driven changes in snowfall patterns also matter. If certain regions accumulate more snow in winter and less in summer than before, seasonal mass distribution changes slightly. All of these processes combine into a constantly evolving pattern of shifting weight across the planet. When scientists analyze rotation changes, they incorporate data from satellite missions that measure gravity and mass distribution. Satellites like those in the GRACE mission detect tiny changes in Earth's gravitational field caused by mass movements. By comparing these data with changes in the length of the day, researchers can estimate how much of the observed acceleration might be linked to surface mass redistribution. The conclusion so far is that melting ice and shifting weight likely play a supporting role in the recent speeding up of Earth's rotation, but they are not the sole cause. The cause subtle dynamics, atmospheric circulation, and ocean patterns also contribute. The observed acceleration appears to be the result of multiple influences acting in the same direction over a span of years. There is also a time lag effect to consider. Earth's response to melting ice is not immediate. The mantle flows slowly. The crust rebounds gradually. The redistribution of water interacts with ocean circulation patterns. These processes overlap in time, creating complex signals in rotation data. This makes it challenging to isolate one factor from another. What makes melting ice particularly interesting in this context is that it ties Earth's rotation to climate variability. The cryosphere, the the frozen portion of the planet is not isolated from rotational dynamics. Changes at the poles can influence the entire planet's spin. Again, this does not imply a dramatic change in daily life. The length of a day remains very close to 24 hours. The differences are measured in thousandths of a second. But the connection is conceptually powerful. The melting of ice, something visible and tangible in the world, is linked through physics to the motion of the entire planet. As we continue this exploration, it becomes increasingly clear that Earth's rotation is a summary of everything happening within and on the planet. The core moves, the mantle flows, the oceans circulate, the atmosphere shifts, ice grows and melts. Each process nudges the rotation slightly. Above your head, even on the calmest night, the atmosphere is never still. Air is always moving, sliding past itself in layers, circling the planet in vast looping paths that stretch from equator to pole and back again. We tend to think of wind as something local, a breeze through trees, a gust against a window, a weather report detail. But on a planetary scale, wind is one of the largest moving systems Earth has, and because it moves so much mass so quickly, it carries momentum. That momentum matters. When scientists began comparing Earth's rotation speed with atmospheric data, they noticed something intriguing. Changes in wind patterns often coincided with small changes in the length of the day, not by accident, not by coincidence, but because the atmosphere and the solid Earth are physically linked through the same rule that governs everything else in this story: conservation of angular momentum. To understand how wind can influence the rotation of an entire planet, it helps to start with something familiar. If you are sitting on a spinning chair and you swing your arms back and forth, you do not just move your arms, the chair responds. If your arms speed up in one direction, the chair subtly shifts in the opposite direction. That happens because the total angular momentum of the system must remain constant unless an external force acts on it. Earth and its atmosphere behave like that chair and arms system. The atmosphere is not separate from Earth's rotation. It is already moving eastward with the planet because it is in contact with the surface. When winds blow eastward faster than average, the atmosphere gains angular momentum. To compensate, the solid Earth must lose a small amount of angular momentum, slowing its rotation slightly. When winds weaken or shift westward, the atmosphere loses angular momentum and the solid Earth gains it, speeding up slightly. This exchange happens all the time. The atmosphere contains about 5 quintillion kilograms of air. That may sound small compared to the mass of Earth, but what matters is speed and distance from the axis. Much of the atmosphere's motion occurs far from the axis, especially in the tropics, where Earth's surface moves fastest due to rotation. Small changes in wind speed across large areas can have measurable effects. Scientists track something called atmospheric angular momentum, which quantifies how much rotational momentum the atmosphere carries at any given time. This value fluctuates daily, seasonally, and over longer cycles. When atmospheric angular momentum increases, Earth's rotation slows slightly. When it decreases, Earth speeds up slightly. Seasonal patterns alone are enough to cause detectable changes in the length of the day. During certain times of year, global wind patterns shift in ways that alter angular momentum exchange. For example, in the northern hemisphere winter, stronger westerly winds tend to develop at mid-latitudes. These winds increase atmospheric angular momentum. As a result, Earth's rotation slows by a small amount, lengthening the day by a fraction of a millisecond. In summer, the pattern often reverses, and Earth speeds up slightly. These seasonal variations are well understood and predictable. They have been measured for decades, but the atmosphere does more than follow simple seasonal cycles. Large-scale climate patterns can reorganize wind systems across entire ocean basins. One of the most influential of these patterns involves shifts in tropical Pacific winds. When these winds strengthen or weaken, the redistribution of atmospheric angular momentum can be substantial. During certain phases of these patterns, trade winds intensify, pushing air masses westward near the equator. This reduces atmospheric angular momentum and allows Earth's solid body to spin slightly faster. During opposite phases, winds relax or reverse, increasing atmospheric angular momentum and slowing Earth's rotation slightly. These effects are subtle but consistent. Over periods of months to years, atmospheric circulation can remain in configurations that favour either acceleration or deceleration of Earth's rotation. This is one reason why the shortest days on record tend to cluster rather than appear randomly. Atmospheric conditions can persist for extended periods, reinforcing the same rotational effect day after day. Another important factor is how wind patterns interact with altitude. Not all air moves at the same speed. The jet streams, narrow bands of fast-moving air high in the atmosphere, carry enormous amounts of momentum. Shifts in the position or strength of these jet streams can alter atmospheric angular momentum significantly. When jet streams weaken or shift poleward, the net angular momentum of the atmosphere can decrease. That decrease is transferred to the solid Earth. Even changes in stratospheric winds, far above weather systems we experience directly, can influence rotation. Sudden stratospheric warming events, for example, can disrupt typical wind patterns and temporarily alter angular momentum exchange. These events are rare, but their effects ripple downward through the atmosphere and into rotation measurements. It is also important to remember that the atmosphere does not move independently of the oceans. Winds drive ocean currents. Ocean temperatures influence wind patterns. This coupling means that atmospheric and oceanic contributions to rotation often reinforce or counteract each other. In some periods, winds and currents align in ways that both contribute to acceleration. In others, they oppose each other, muting the net effect. Recent studies suggest that changes in global wind patterns over the past few years have contributed to a reduction in atmospheric angular momentum. That reduction would naturally lead to a slight increase in Earth's rotation speed. This does not mean winds suddenly changed in an unprecedented way. It means that within normal variability, the atmosphere entered a state that favoured acceleration. Again, the scale is important. We are not talking about storms or gusts. We are talking about average wind behaviour integrated across the entire planet. These are whispers, not shouts. Another subtlety lies in how friction connects the atmosphere to the surface. Air does not slide freely over Earth. Friction with mountains, forests, cities, and the ocean's surface constantly transfers momentum. When winds slow due to friction, momentum is transferred to the solid Earth. This frictional coupling is strongest near the surface, but its cumulative effect is global. Changes in surface roughness, vegetation, snow cover, and sea ice can alter friction slightly. Over large areas, even small changes in friction can affect how efficiently momentum is exchanged. Sea ice loss, for example, exposes more open water. Open water has different frictional properties than ice. This alters wind stress and momentum transfer between air and ocean. Once again, nothing dramatic, but part of a larger pattern. One of the challenges in studying atmospheric effects on Earth's rotation is separating cause from coincidence. Wind patterns change constantly. Rotation varies constantly. Correlations must be tested carefully. Scientists use long-term data sets, combining atmospheric reanalysis data with precise rotation measurements. By comparing changes in atmospheric angular momentum with changes in the length of the day, they can identify consistent relationships. These studies show that atmospheric changes can account for a significant portion of the short-term rotation variability, especially on timescales from days to years. They cannot explain everything. Core dynamics and ocean circulation are still needed to account for longer-term trends and deeper oscillations. But the atmosphere is a major player. It is also the fastest-moving large-scale system involved. Changes that would take years in the mantle or decades in the core can happen in the atmosphere in weeks. This makes the atmosphere especially relevant when examining clusters of short days. If wind patterns favour acceleration for an extended period, the effect can persist long enough to set records. Another reason atmospheric effects matter is that they are closely monitored. Weather models track wind speeds, directions, and pressures with high resolution. This allows scientists to test hypotheses about rotation changes in near real time. When a particularly short day occurs, researchers can look at atmospheric angular momentum data and ask whether winds were behaving in a way that would explain it. Often, the answer is at least partly yes. That said, the atmosphere alone does not fully explain the recent acceleration. Its influence is strongest over short timescales. The fact that the acceleration has persisted across multiple years suggests that deeper processes are also involved. Still, the atmosphere provides a crucial piece of the puzzle. It reminds us that Earth's rotation is not governed solely by deep, hidden mechanisms. It is influenced by the moving air above us, by patterns that shape weather and climate, by forces we experience every day without realizing they extend all the way to planetary motion. The idea that winds can nudge the world may sound poetic, but in physics it is literal. Momentum moves, it must go somewhere. When air speeds up or slows down, Earth responds. Most of the forces we've explored so far move slowly. The moon pulls steadily over billions of years, ice sheets grow and melt over centuries, ocean currents shift over months, winds adjust over seasons, even the deep core's oscillations unfold across decades. But occasionally the planet changes shape in an instant. An earthquake does not politely redistribute mass over time. It breaks rock. It shifts entire sections of crust in seconds. It releases energy that has been building for years or centuries, and when that happens, Earth's shape changes, if only slightly. When Earth's shape changes, so does its rotation. This might sound dramatic, but the effect is very small. Earthquakes do not shorten days by noticeable amounts. They do not alter sunrise times in ways we could perceive. The changes they cause are measured in microseconds, not milliseconds. Still, they are measurable. To understand how an earthquake can influence rotation, we need to return once more to the principle of mass distribution. Earth's rotation speed depends on its moment of inertia, which depends on how mass is arranged relative to the axis. If a large earthquake shifts mass slightly closer to the axis, Earth spins a bit faster. If mass shifts farther away, Earth spins a bit slower. Major earthquakes involve the movement of enormous blocks of crust. Tectonic plates slide past one another, collide, or pull apart. When stress along a fault exceeds the strength of the rock, it snaps, and the crust shifts by meters over areas hundreds of kilometers long. Even though the movement seems localized compared to the size of the planet, the mass involved is vast. Consider one of the largest earthquakes in recent history, the 2004 Indian Ocean earthquake. It had a magnitude of approximately 9.1 to 9.3 and involved the movement of a massive section of the seafloor. Scientists calculated that this earthquake likely shortened the length of the day by about 2.7 microseconds. That is less than 3 millionths of a second. Another large earthquake, the 2011 Tohoku earthquake in Japan, with a magnitude of 9.0, is estimated to have shortened the day by about 1.8 microseconds. These numbers are tiny, but they are not zero. They reflect a real change in the planet's distribution of mass. The reason these earthquakes shorten the day rather than lengthen it is related to the geometry of the fault movement. In both cases, sections of crust shifted slightly closer to the axis of rotation. That reduced Earth's moment of inertia, causing a slight increase in rotation speed. Not all earthquakes have the same effect. The direction of fault slip matters. Whether mass moves toward or away from the axis depends on the specific tectonic setting. Most earthquakes are too small to have a measurable global rotational effect. Only the largest events produce changes detectable with modern instruments. Even then, the effect is far smaller than the millisecond level variations associated with atmospheric or oceanic processes. So why include earthquakes in this story at all? Because they illustrate something important. Earth's rotation responds to any redistribution of mass, regardless of how that redistribution occurs. An earthquake is a sudden reminder that the planet is not rigid. The crust can move abruptly, the mantle can adjust, energy stored over long periods can be released in seconds. When that happens, the change is recorded not only in seismic waves and damaged buildings, but in the timing of Earth's rotation. There is another subtle aspect to consider. Earthquakes do not only shift mass horizontally, they also involve vertical displacement. Sections of crust can rise or sink by meters. This alters the shape of Earth very slightly. Changes in Earth's shape influence its moment of inertia. Imagine compressing a spinning ball very slightly along one axis. Its rotation changes. The same principle applies to Earth. However, it is important to keep perspective. The cumulative effect of all major earthquakes over a decade is still smaller than the influence of atmospheric and oceanic variations over the same period. Earthquakes are episodic. Winds and currents are continuous. Earthquakes contribute noise to the rotation record, not the dominant signal. There is also the question of whether increased seismic activity in certain periods could explain clusters of shorter days. So far, the evidence suggests that earthquakes alone cannot account for the recent acceleration. The timing and magnitude of the shortest days do not correlate strongly enough with major seismic events to explain the pattern. Still, each large earthquake adds a tiny adjustment. It is also worth noting that earthquakes can affect the orientation of Earth's axis slightly. Large quakes can cause polar motion, small shifts in the position of the rotation axis relative to the crust. These shifts are measured in centimeters. Polar motion does not directly change the length of the day, but it reflects changes in mass distribution and can be part of the broader rotational picture. Another way to think about earthquakes in this context is as brief interruptions in an otherwise gradual story. Most of the time, Earth's rotation changes smoothly. Atmospheric angular momentum increases or decreases over days. Ocean circulation shifts over months. Core dynamics evolve over years. An earthquake is a step change, a tiny twitch in the planet's rotation that happens almost instantaneously. These twitches accumulate over time, but they do not drive long-term trends. They do, however, remind us that Earth is not a perfectly uniform, stable object. It is fractured. It is dynamic. It stores stress and releases it unpredictably. The fact that we can measure the rotational consequences of such events speaks again to the precision of modern timekeeping. Without atomic clocks and astronomical measurements, the microsecond changes caused by earthquakes would remain unnoticed. And yet, even with that precision, we can say with confidence that earthquakes are only a small part of the recent speeding up story. They are contributors, but not leaders. What becomes clear as we layer these influences together is that Earth's rotation is shaped by processes operating on very different timescales. The Moon slows rotation over billions of years. Ice and mantle rebound alter it over centuries. Core oscillations shift it over decades. Atmospheric and oceanic patterns change it over months. Earthquakes adjust it in seconds. Each layer adds its own signature. The recent record-setting short days likely reflect a combination of influences rather than a single dramatic cause. When we have talked about winds nudging the world, oceans redistributing weight, ice sheets melting and crust rebounding, and even earthquakes giving the planet a tiny twitch, one idea has quietly connected all of those pieces. It has appeared again and again, sometimes briefly, sometimes more directly. That idea is angular momentum. If we want to understand why Earth can spin slightly faster at certain times, despite the Moon's steady braking over billions of years, then we need to slow down and understand angular momentum clearly. Not as an abstract formula, not as a line in a physics textbook, but as something intuitive and physical. Angular momentum is simply the quantity that describes how much rotational motion an object has. It depends on two things: how fast the object is rotating and how its mass is distributed relative to the axis of rotation. The faster something spins, the greater its angular momentum. The farther its mass is from the axis, the greater its angular momentum. Both factors matter. There is also a rule that governs angular momentum. In a closed system, angular momentum must be conserved unless an external torque acts on it. That means the total amount cannot change unless something outside the system applies a twisting force. For Earth, the Moon provides such a torque. That is why, over billions of years, Earth's rotation has slowed. The Moon's gravity applies a steady external torque through tidal friction. But within the Earth system itself, among the core, mantle, oceans and atmosphere, angular momentum is exchanged rather than created or destroyed. This is where the comparison to a spinning figure skater becomes useful. Imagine a skater on ice, spinning with arms extended. When their arms are stretched outward, their mass is distributed farther from their axis of rotation. Their moment of inertia, which is a measure of how mass is distributed, is relatively large. Because angular momentum must be conserved, and because no external torque is acting, their rotation speed adjusts accordingly. Now picture the skater pulling their arms inward toward their chest. Their mass shifts closer to the axis. Their moment of inertia decreases. Since angular momentum must stay the same, their rotation speed increases. They spin faster. No new energy was added. Nothing pushed them. The change happened because of mass redistribution. That is the essential physics behind many of the changes in Earth's rotation speed. Earth is not a rigid bowling ball. It is more like a layered, partially fluid skater. When mass moves closer to the axis, rotation increases. When mass moves outward, rotation decreases. The formal relationship is expressed in a simple equation. L equals I times omega. Here, L represents angular momentum, I represents moment of inertia, and omega represents angular velocity, or rotation speed. If no external torque acts, L remains constant, so if I decreases, omega must increase. If I increases, omega must decrease. For Earth, I changes whenever mass is redistributed. Let's make this concrete. When strong westerly winds accelerate in the atmosphere gains angular momentum. Because total angular momentum must be conserved, the solid Earth loses some and rotation slows slightly. When those winds weaken, the atmosphere loses angular momentum and the solid Earth gains some, spinning slightly faster. The same principle applies to oceans. When ocean currents shift water toward the equator, the planet's moment of inertia increases because mass moves farther from the axis. Earth slows slightly. When water shifts poleward, moment of inertia decreases and Earth speeds up slightly. Melting ice is another example. If ice mass concentrated near the poles melts and spreads toward lower latitudes, moment of inertia increases. Earth slows. If crust rebounds and mantle flows redistribute mass inward toward the axis, moment of inertia decreases. Earth speeds up. Earthquakes can also change I. If a major fault shifts rock close to the axis, I decreases and omega increases. Every example follows the same rule. What makes Earth's case more complex than the skater is that there are multiple subsystems interacting simultaneously. The atmosphere exchanges angular momentum with the surface. The oceans exchange angular momentum with both atmosphere and crust. The liquid outer core can exchange angular momentum with the mantle. Even electromagnetic coupling between the core and mantle can transfer momentum. These exchanges are continuous. Now consider the system as a whole. If we treat Earth and its atmosphere as a closed system, total angular momentum remains nearly constant over short timescales. The Moon's torque acts slowly over millions of years, but over days, months, or years, the exchanges are internal. When one part speeds up, another must slow down. This conservation principle is what allows scientists to predict and interpret rotation changes. For example, atmospheric angular momentum can be calculated from global wind data. If atmospheric angular momentum drops, we expect Earth's rotation to increase slightly. And that is exactly what measurements show. The agreement between predicted and observed changes reinforces the central role of angular momentum conservation. There is another layer to this. Earth is not a perfect sphere. It bulges slightly at the equator due to rotation. This equatorial bulge increases its moment of inertia compared to a perfect sphere. If Earth's shape changes even slightly, moment of inertia changes. Glacial rebound, for example, can alter Earth's shape. When crust rises near the poles, mass moves slightly closer to the axis. That reduces I and increases omega. Over long timescales, tectonic plate motions can also alter Earth's mass distribution. Continents drifting toward or away from the equator change a wee. However, these tectonic effects are extremely slow. The more immediate contributors to recent acceleration are atmospheric, oceanic, and possibly correlated. Now consider what would happen if Earth were perfectly rigid and nothing moved internally. In that case, once formed, its rotation speed would only change due to external torques like the Moon's tidal friction. There would be no short-term variability. But Earth is dynamic. The atmosphere alone carries enormous angular momentum. Jet streams at high altitude move at speeds exceeding 100 km per hour over thousands of kilometers. Multiply that by the mass of air involved, and you get a significant contribution. Ocean currents like the Gulf Stream transport millions of cubic meters of water per second. That water is not stationary. It moves relative to the surface and exchanges momentum. The outer core contains liquid iron moving under extreme pressure and temperature. Its flows are not visible, but they carry angular momentum that can be transferred to the mantle. Because these subsystems move differently at different times, Earth's surface rotation reflects the balance among them. Another way to think about this is in terms of coupling. The atmosphere is loosely coupled to the surface through friction. The oceans are more strongly coupled through both friction and pressure. The core is coupled through gravitational and electromagnetic interactions. The strength of coupling determines how efficiently angular momentum is exchanged. If atmospheric winds change rapidly, the effect on rotation can appear quickly, because friction transfers momentum. If core flows change, the effect may take longer to manifest because the coupling is weaker. The recent speeding up of Earth's rotation likely reflects a period in which multiple subsystems reduced their angular momentum relative to the solid Earth. If atmospheric angular momentum decreased, while ocean circulation patterns favoured inward mass redistribution, and core dynamics transferred momentum outward to the mantle, the combined effect would be acceleration. Each factor alone might produce a small change. Together they can produce record short days. It is important not to exaggerate the magnitude. The changes observed are measured in milliseconds. 1 millisecond is 1,000th of a second. A 1.5 millisecond shortening of a day means that instead of 86,400 seconds, the day lasted 86,399.9985 seconds. This difference accumulates slowly. It does not disrupt daily life, yet it is real. And the fact that it follows the logic of angular momentum conservation so precisely is reassuring. There is no violation of physics. There is no unexplained force. There is only redistribution. The cosmic ice skater analogy remains useful. Imagine the skater not as a single rigid body, but as wearing flowing sleeves, carrying water buckets, and standing on a flexible platform. As they move their arms, as water sloshes, as fabric shifts, their rotation speed adjusts constantly. That is Earth. The platform is the mantle, the water buckets are the oceans, the flowing sleeves are the atmosphere. Deep inside a hidden mechanism, the core shifts weight subtly from time to time. The moon stands outside the rink, gently tugging, slowing the spin over the very long term. All of it obeys the same equation. Understanding this, physics clarifies why Earth can spin slightly faster, even while tidal friction continues to act. Over short timescales, internal redistributions dominate. Over long timescales, external torques win. Right now, We appear to be in a period where internal redistributions are nudging the planet in the accelerating direction. This does not mean the long-term slowing has reversed. It means the skater has briefly pulled their arms inward while still gradually losing energy to the outside. As we continue this exploration, it will be helpful to connect this physics to human timekeeping directly. Because when Earth's rotation fluctuates, even slightly, we are faced with a practical question. If atomic clocks remain steady and Earth does not, which one should define the day? When we began this journey, we spoke about Earth's rotation as something ancient and steady, something that quietly gives us day and night. Then we uncovered something subtle. Earth does not rotate with perfect consistency. It slows over long timescales. It fluctuates over shorter ones. Winds shift, oceans circulate, ice melts, the core moves, and all of it leaves tiny fingerprints on the length of a day. But here is the practical problem. Our clocks do not tolerate fluctuation. For most of human history, that was not an issue. Sundials drifted naturally with the sun. Mechanical clocks were imprecise enough that small irregularities in Earth's rotation went unnoticed. Even quartz clocks for decades were close enough to solar time that nobody worried about milliseconds. Then atomic clocks arrived. Atomic clocks do not care about Earth's rotation. They measure time using the natural oscillations of atoms, usually cesium. 1 second is defined as exactly 9,192,631,770 oscillations of a specific cesium transition. That definition does not stretch or shrink depending on winds or tides. It is constant. So now we have two different clocks. One is atomic time, which ticks perfectly steadily. The other is Earth rotation time, which wobbles slightly. For everyday purposes, the difference is microscopic, but over time it accumulates. If Earth rotates slightly slower than atomic time suggests, then solar noon, the moment when the sun is highest in the sky, will drift relative to our clocks. Over years, the drift grows. Without correction, noon would slowly move away from the middle of the day. The solution humanity chose is called the leap second. A leap second is an adjustment occasionally inserted into Coordinated Universal Time, or UTC, to keep atomic time aligned with Earth's rotation. When Earth runs slightly slow, an extra second is added. That means 1 minute briefly has 61 seconds instead of 60. This sounds simple, but it is an extraordinary decision. We have chosen to adjust our official timekeeping system to match the imperfect variable rotation of a planet. The first leap second was introduced in 1972. Since then, more than 24 leap seconds have been added. Most of them occurred because Earth's rotation was slightly slower than atomic time. Each time the difference between atomic time and Earth rotation time approached about 0.9 seconds, a leap second was inserted to bring them back into alignment. The adjustments are coordinated internationally. Organizations monitor Earth's rotation continuously. When the difference grows too large, they announce that a leap second will be added at the end of June or December. On that day, clocks display 23:59:59, then 23:59:60, then 000000. It is a small pause, a tiny moment where humanity acknowledges that the planet beneath us does not spin with perfect precision. For decades, the pattern was consistent. Earth's rotation, influenced by tidal breaking from the moon, was gradually slowing. Leap seconds were added to compensate. Then something unusual happened. In recent years, Earth began spinning slightly faster relative to atomic time. That raised a new possibility. What if, instead of adding a leap second, we needed to subtract one? This would be called a negative leap second. It has never been done. A negative leap second would mean skipping a second. Instead of counting from 23:59:58 to 23:59:59 to 000000, clocks would jump directly from 23:59:58 to 000000, omitting 23:59:59 entirely. From a physics perspective, this is simply the mirror image of adding a second. From a technical perspective, it is far more complicated. Modern computer systems, financial networks, GPS satellites, telecommunications infrastructure, and countless digital systems rely on precise time synchronization. Many of these systems were designed to handle positive leap seconds because those were historically necessary. Few were designed with negative leap seconds in mind. Adding a second is already disruptive for certain systems. Subtracting one introduces new challenges. There have been instances in the past where leap seconds caused glitches. Some computer systems froze or behaved unpredictably during the extra second. Engineers have had to develop methods for smearing leap seconds, gradually adjusting clocks over a longer interval rather than inserting a sudden jump. The discussion about negative leap seconds highlights something important. Our modern world depends on atomic time. Global positioning systems rely on extremely precise timing to calculate location. GPS satellites orbit Earth and carry atomic clocks. By comparing the arrival times of signals from multiple satellites, a receiver can determine its position. If the timing is off by even microseconds, location errors grow. Financial markets timestamp transactions to fractions of a second. Data centers synchronize operations across continents. Telecommunications networks coordinate signals at high speed. All of this depends on stable, uniform time. And yet, our definition of the day, culturally and historically, is tied to Earth's rotation. There is a tension here. Atomic time is perfectly steady but disconnected from the Sun. Earth rotation time aligns with the Sun but fluctuates. Leap seconds are a compromise. They allow us to keep civil time close to solar time while using atomic clocks as the foundation. However, because Earth's rotation variability has become more noticeable with improved measurement, and because leap seconds are technically inconvenient, there has been debate about whether to continue using them. Some organizations have proposed eliminating leap seconds altogether and allowing atomic time to drift gradually away from Earth rotation time. Under that approach, no more leap seconds would be added or subtracted. The difference would accumulate slowly. It would take centuries for noon to drift noticeably away from midday. The debate reflects how our relationship with time has changed. For most of history, the sun defined the day. Now, atoms define the second. Earth's recent speeding up has added urgency to this discussion. If rotation continues to fluctuate unpredictably, managing leap seconds becomes more complex. It is important to remember that the speeding up is small. We're talking about milliseconds per day. It would take hundreds of days of consistent acceleration to eliminate the need for a leap second, and many more to require a negative one. Still, the fact that negative leap seconds are being discussed at all is historically significant. It means Earth's rotation is no longer assumed to be steadily slowing on human timescales. It means variability is not just theoretical. There is something quietly profound about leap seconds. They are moments when human timekeeping bows slightly to planetary physics. For 1 second, literally, the entire world adjusts. No alarm sounds, no one feels it. But in laboratories and data centers around the globe, clocks tick differently for a brief instant. This adjustment reminds us that our schedules, our calendars, our synchronized networks all rest on a moving foundation. It also highlights how delicate our timekeeping system has become. We measure time more precisely than ever before. But the reference frame we once trusted, Earth's rotation, is not perfectly stable. It becomes natural to ask what might happen if Earth continued to speed up for an extended period. Would leap seconds disappear entirely? Would days become measurably shorter over decades? Or is the recent acceleration just one phase in a longer oscillation, destined to reverse as other forces take over? Because while leap seconds represent humanity's adjustment to the planet, the deeper question remains, is this speeding up temporary or part of something larger? Imagine waking up one morning and nothing feels different at all. Your alarm rings when it always does. The light through the window looks familiar. Your body moves at its usual pace, and yet, without any sensation, without any signal your senses could detect, the planet beneath you is turning a little faster than it used to. That thought sits at the centre of an intriguing question. What if Earth did not slow back down? What if the recent acceleration were not a brief fluctuation, but the beginning of a longer period where rotation continued to speed up? To be clear from the outset, this is not a prediction. It is a thought experiment, a way of understanding what rotation really means for a planet like Earth, and how deeply it is woven into systems we rarely think about until something nudges them out of alignment. The first thing worth addressing is scale. Even the fastest days ever recorded have been shorter by only about 1.5 milliseconds. That is 1,000th of a second. If Earth continued speeding up at that rate every single day, which is extremely unlikely, it would still take hundreds of days to shorten the length of a day by 1 full second. And even 1 second spread across an entire planet is subtle, so nothing sudden happens. There is no moment where people stumble because the ground is moving too fast. There is no sudden change in gravity. Earth's rotation is already fast at the equator, about 1,670 kilometers per hour, and a change of a few milliseconds does not meaningfully alter that experience. Still, over long periods, small changes accumulate. If days became consistently shorter, the most immediate effects would not be physical, but temporal. They would show up first in clocks. Atomic clocks would continue ticking at the same rate. They do not care what Earth does, but Earth rotation time would drift in the opposite direction than it has for most of modern history. Instead of Earth lagging behind atomic time, it would gradually move ahead of it. That would force a decision. Either timekeeping systems would have to adjust by removing leap seconds, or humanity would have to accept that civil time slowly drifts away from solar time. If Earth kept speeding up enough to require negative leap seconds, the adjustment would be technically challenging but manageable. Systems would need to skip a second occasionally. Engineers would adapt. Time servers would update their protocols. It would be inconvenient, not catastrophic. But if acceleration continued for decades, leap seconds might disappear altogether. Atomic time and civil time could remain aligned without adjustment. That might sound tidy, but it would represent a historical reversal. For centuries, our clocks have slowly chased a slowing Earth. A speeding Earth would flip that relationship. Beyond clocks, there is the question of day-night cycles. Shorter days mean faster sunrises and sunsets. But again, the effect would be tiny. A millisecond difference does not shift sunrise in any perceptible way. Even a full second difference would change sunrise times by 1 second, which no one would notice without checking a precise instrument. Over centuries, however, cumulative changes could add up to minutes, over millennia, hours. But such timescales far exceed any realistic projection of sustained acceleration. Still, thinking about the implications helps clarify how rotation influences life. Earth's rotation affects atmospheric circulation. The Coriolis effect depends on rotation speed. Faster rotation strengthens the Coriolis force. That can influence wind patterns, storm tracks, and ocean currents. If Earth rotated significantly faster, atmospheric circulation would look different. Jet streams would shift. Weather systems would organize differently. Storms might become narrower and more intense in some regions. But again, the key word is significantly. A change of milliseconds does not meaningfully alter the Coriolis effect. You would need a much larger change, on the order of hours, to see noticeable climatic differences. Earth has experienced such changes in the deep past. When days were shorter hundreds of millions of years ago, atmospheric and oceanic circulation patterns were indeed different. But those changes unfolded over geological timescales, allowing ecosystems to adapt. In the context of current observations, none of that is imminent. Another question people often ask is whether faster rotation would change gravity. Rotation creates a slight centrifugal effect that reduces effective gravity at the equator. That effect already exists. Gravity at the equator is slightly weaker than at the poles. If Earth spun faster, that effect would increase slightly. But once again, the changes we are discussing are far too small to notice. You would not weigh less in any meaningful way. To change gravity perceptibly, Earth would need to rotate dramatically faster, far beyond anything suggested by current trends. There is also the question of Earth's shape. Rotation causes Earth to bulge at the equator. Faster rotation would increase that bulge. Slower rotation would allow Earth to become more spherical. The current equatorial bulge is about 21 kilometers greater than the polar radius. A millisecond level change in rotation speed would alter that bulge by amounts far smaller than any measurement outside of geodetic instruments. So again, nothing dramatic. Which raises an important point. If Earth kept speeding up, most of the consequences would remain confined to precision systems, not everyday experience. Timekeeping would notice first, navigation systems would adjust, astronomical observations would recalibrate, scientists would track the change carefully. For most people, life would feel exactly the same. This often leads to a deeper realization. Earth's rotation matters enormously, but only because we have built systems that measure it with extraordinary precision. Our ancestors lived their entire lives without knowing that days varied by milliseconds. They experienced sunrise and sunset as constants. It is only because our technology has become so precise that these variations matter. Still, sustained acceleration would prompt scientists to look for deeper explanations. If Earth were to keep speeding up beyond short-term fluctuations, it would suggest that internal or surface processes were consistently redistributing mass inward toward the axis. That could point to long-term changes in core dynamics, mantle flow, or climate-driven mass redistribution. Such a pattern would not be dangerous, but it would be scientifically fascinating. It would provide insight into processes happening deep inside the planet. Another consideration is the Moon. If Earth sped up significantly, tidal interactions would change slightly. The Moon's braking effect would still operate, but the balance between Earth's rotation and the Moon's orbit would adjust. In practice, the Moon's influence is so dominant over long timescales that it would eventually counteract sustained acceleration. Tidal friction does not disappear. It always acts to slow Earth's rotation. That makes it unlikely that Earth could continue speeding up indefinitely. What we are more likely seeing, and what most models suggest, is a temporary oscillation, a period where internal redistributions and surface processes temporarily outweigh tidal braking. Eventually, those processes shift, atmospheric patterns change, ocean circulation reorganizes, core dynamics evolve, the balance tips back, Earth slows again. This oscillatory behavior is consistent with historical data. Length of day records show variations over decades, with periods of relative acceleration and deceleration superimposed on the long-term slowing trend. In that sense, the question, what if Earth kept speeding up, is useful not because it predicts the future, but because it clarifies boundaries. It shows us that Earth's rotation is stable enough that even measurable acceleration does not threaten planetary systems. It also shows us that variability is normal. Another interesting aspect is psychological. Humans tend to associate acceleration with danger. A car accelerating too fast can be unstable. A spinning object accelerating can fly apart. But planetary rotation does not work that way within these ranges. Earth has enormous structural integrity. The forces involved in millisecond-level changes are trivial compared to the forces Earth already withstands. There is no scenario in which Earth spins itself apart due to these fluctuations. In fact, if Earth rotated significantly faster, closer to its early history, life might still exist, just adapted differently. Shorter days would alter circadian rhythms, but biology adapts over time. Again, this is not something happening now. It is a reminder of Earth's resilience. The more subtle implication of continued acceleration lies in how we define time. If Earth's rotation were to remain unpredictable, it would strengthen arguments for decoupling civil time from solar time entirely. Atomic time could become the sole reference. Solar time would become an astronomical concept rather than a practical one. That would be a cultural shift. For thousands of years, the day has been defined by the sun's motion. Even now, our clocks are tied indirectly to Earth's rotation through leap seconds. A future without leap seconds would mark a philosophical change as much as a technical one. Time would be something defined entirely by atoms, not by the turning of the world. Whether that happens or not depends less on Earth's behaviour than on human choice. The debate is ongoing. What remains clear is that Earth's recent speeding up does not signal a runaway process. It is part of a dynamic system responding to multiple influences. If acceleration continued for a while, scientists would document it. Engineers would adapt timekeeping systems. Life would go on. Eventually, other forces would assert themselves, and the balance would shift again. Has Earth experienced periods of faster rotation in the past that resemble what we see now? And if so, what caused them? Long before atomic clocks existed, long before anyone could count milliseconds or worry about leap seconds, Earth was already changing the length of its days. Not once, not recently, but repeatedly, quietly, across spans of time so long that no single moment could ever stand out as unusual. From that perspective, the question is not whether Earth's rotation has behaved differently before, but how often it has done so, and whether what we are seeing now fits into a familiar pattern rather than a novel one. To answer that, we have to loosen our grip on the modern idea of a normal day. The 24-hour day feels fundamental because it frames our lives. It defines sleep, work, light, darkness, and routine. But it is not fixed by any deep rule of the universe. It is simply the current state of a spinning planet that has been changing since the moment it formed. Early Earth rotated much faster than it does today. That is not speculation. It is a consequence of physics and supported by multiple independent lines of evidence. When Earth formed from a collapsing disk of material around the young sun, that material already carried angular momentum. As it condensed into a planet, its rotation speed increased, just as a collapsing cloud spins faster as it shrinks. In those earlier stages, a day may have lasted only a few hours. The moon-forming impact likely altered Earth's rotation significantly. A massive collision would have redistributed angular momentum between Earth and the debris that later became the Moon. The newly formed Earth-Moon system would have been far more compact and energetic than it is now. From that point onward, the long process of tidal braking began. As we explored earlier, the Moon's gravitational pull created tides that dissipated energy and gradually slowed Earth's rotation. Over billions of years, this stretched days from just a few hours to something approaching the familiar rhythm we know, but that slowing was not smooth. The evidence for variable day length comes from geology itself. Certain ancient organisms recorded time in their bodies. Corals, stromatolites, and some shell-forming creatures grew in daily layers, influenced by sunlight and tides. These growth patterns were preserved in fossils. By counting daily layers within yearly growth cycles, scientists can determine how many days made up a year at different points in Earth's past. Those fossils tell a clear story. Hundreds of millions of years ago, there were more days in a year than there are now. During the Devonian period, roughly 400 million years ago, a year may have contained about 400 days. That means each day was shorter, roughly 21 to 22 hours long. Go back even further, and days were shorter still. This confirms the long-term slowing trend driven by tidal friction. But within that trend, there were variations. Geological records show that the rate of slowing itself has changed over time. That is not surprising. The Moon was closer in the past, exerting stronger tidal forces. As it moved farther away, those forces weakened. The rate of slowing decreased. At the same time, Earth itself was changing. Continents assembled and broke apart. Supercontinents formed and dispersed. Ice ages came and went. Sea levels rose and fell, the mantle cooled, the core evolved. Each of these processes altered Earth's mass distribution. When supercontinents formed near the equator, mass moved farther from the axis, increasing moment of inertia and slowing rotation slightly. When continents fragmented and drifted poleward, the opposite could occur. Ice ages had particularly noticeable effects. When massive ice sheets covered large portions of the continents near the poles, mass concentrated closer to the rotation axis. That would have caused Earth to spin slightly faster than it otherwise would have at that time. When those ice sheets melted, water spread toward lower latitudes, slowing rotation again. These changes were small compared to the overall slowing, but they mattered. They mean that Earth's rotation history is not a simple, smooth curve. It is a curve with bumps, plateaus, and oscillations. On shorter timescales, even historical observations reveal variability. Before atomic clocks, astronomers relied on careful observations of celestial motions to keep time. By tracking the positions of the moon, planets, and stars, they could infer how Earth's rotation behaved. When modern scientists compared historical eclipse records with modern calculations, they found discrepancies that could only be explained by changes in Earth's rotation speed. Ancient records of eclipses from Babylonian, Chinese, and Greek sources did not line up perfectly with modern predictions unless Earth's rotation was adjusted. These adjustments reveal that Earth's rotation has not slowed uniformly. There were periods when it slowed more quickly, and periods when it slowed less. In some intervals, it may even have experienced brief accelerations relative to the long-term trend. The key point here is that variability is not new. What is new is our ability to measure it directly and continuously. In the past, changes had to be inferred indirectly from astronomical records spanning centuries. Today, we can detect them day by day. When scientists look at length-of-day records from the past century, they see oscillations on timescales of years to decades. These oscillations are thought to be linked to processes in Earth's core and mantle, as well as interactions with the atmosphere and oceans. One well-known pattern is a roughly 60-year oscillation in Earth's rotation speed. The exact cause is still debated, but it likely involves core-mantle interactions and long-term climate variability. During some phases of this oscillation, Earth rotates slightly faster. During others, it rotates slightly slower. If that oscillation is real and persistent, then the recent acceleration may simply represent one phase of a repeating cycle. That interpretation fits well with what we know. The magnitude of the recent speeding up is not unprecedented when viewed against the backdrop of historical variability. What makes it notable is the precision with which it is measured, and the fact that it has occurred during an era when leap seconds and atomic timekeeping make such changes operationally relevant. There is also the question of whether similar accelerations occurred during previous interglacial periods. After the last ice age, Earth underwent significant glacial isostatic adjustment as ice sheets melted and crust rebounded. That process is still ongoing today, but it was more intense thousands of years ago. It is likely that rotation experienced subtle accelerations during those periods as mass redistributed inward. We cannot measure those accelerations directly, but models suggest they would have occurred. So yes, Earth has experienced changes in rotation speed before. Many times, in many forms. What we're seeing now does not require a new mechanism. It does not require a break from known physics. It fits within a pattern of variability superimposed on a long-term slowing trend. Another way to think about this is to remember that Earth is not seeking a single correct rotation speed. There is no target. The planet responds continuously to changing conditions. Sometimes those conditions align to produce slight acceleration. Sometimes they align to produce slight deceleration. Over very long timescales, the Moon ensures that the net direction is slowing, but over decades, centuries and millennia, fluctuations are inevitable. The present moment feels special because it intersects with human systems that care deeply about precise timekeeping. If we were not using atomic clocks, the recent speeding up might have gone unnoticed. It would not have disrupted agriculture, navigation, or daily life in any way. This highlights an important perspective shift. We're not witnessing an unprecedented planetary event. We are witnessing our own sensitivity to it. That does not make the observation trivial. On the contrary, it makes it valuable. Variations in rotation offer a window into Earth's interior and coupled systems. They provide clues about processes we cannot observe directly. By studying when Earth speeds up and when it slows down, scientists can test models of core dynamics, mantle flow, ocean circulation, and atmospheric behaviour. In that sense, the question, has this happened before, has two answers. Yes, Earth's rotation has varied many times throughout its history, and yes, we have never observed it with this level of precision before. Both statements can be true at the same time. The longer view also tempers any sense of urgency or alarm. The recent acceleration does not signal instability. It does not suggest a runaway process. It does not imply that days will continue shrinking indefinitely. It suggests that Earth is doing what it has always done, adjusting. At first, the idea sounds almost provocative. Climate change influencing Earth's rotation feels like a category mistake, as if something happening in the atmosphere and oceans could not possibly matter for something as fundamental as the spin of an entire planet. After all, climate change is discussed in terms of temperature, weather extremes, ice loss, ecosystems, and sea level. Earth's rotation feels deeper, heavier, more permanent, and yet, once we slow down and follow the physics carefully, the question becomes not only reasonable, but unavoidable, because Earth does not separate its systems neatly. The atmosphere, oceans, ice, crust, mantle, and core are all part of one rotating body. When mass moves anywhere within that body, even at the surface, the rotation responds. So the real question is not whether climate change could influence Earth's spin, but how much influence it could realistically have, and on what time scales. To answer that, we need to be precise. Climate change does not apply an external force to Earth. It does not push the planet or twist it from the outside. There is no new torque being added to the system in the way the moon applies tidal braking. Instead, climate change rearranges mass, and rearranging mass is exactly how rotation speed changes in a closed system. One of the most obvious climate-related mass shifts is melting ice. Glaciers and ice sheets store enormous amounts of mass, much of it concentrated near the poles. As the ice melts, water flows into the oceans and redistributes across the planet's surface. On its own, this outward redistribution of mass toward lower latitudes tends to increase Earth's moment of inertia, which would slow rotation slightly. That effect is real and has been modelled carefully. If this were the only process at work, climate-driven ice melt would make days very slightly longer, not shorter. But as we have already explored, ice melt does not act alone. When ice sheets melt, the crust beneath them rebounds upward. The mantle flows. Mass that was previously displaced outward returns inward. This glacial isostatic adjustment can, over certain timescales, move mass closer to the axis of rotation. That inward shift can partially counteract or even temporarily outweigh the outward movement of water. The net rotational effect depends on the balance between these processes, and that balance is not static. Climate change affects not just ice, but oceans and atmosphere as well. Warming oceans expand. Thermal expansion changes sea level patterns. Ocean circulation adjusts as temperature and salinity gradients shift. Currents strengthen in some regions and weaken in others. These circulation changes redistribute water mass across latitudes and depths. As we discussed earlier, when water mass moves poleward, Earth's rotation can speed up slightly. When it moves equatorward, rotation can slow. Climate change does not produce a uniform redistribution. Some regions warm faster than others. Some currents intensify while others weaken. The result is a complex, evolving pattern of mass movement. At the same time, atmospheric circulation changes. Warming alters pressure gradients, jet streams shift, wind patterns change in both strength and position. These changes affect atmospheric angular momentum. If climate-driven changes lead to a net decrease in atmospheric angular momentum, Earth's solid body must speed up slightly to conserve total angular momentum. If they lead to an increase, Earth slows slightly. Importantly, these atmospheric effects operate on relatively short timescales, from months to years. That makes them especially relevant to recent observations of shorter days. There is evidence that atmospheric circulation patterns over the past few years have favoured reduced atmospheric angular momentum. That would contribute to a small acceleration of Earth's rotation. But here is where caution becomes essential. Climate change is not a single, uniform process. It is a collection of trends and variations superimposed on natural variability. Separating climate-driven effects from natural oscillations is extremely difficult. For example, atmospheric angular momentum varies seasonally and interannually, even in the absence of long-term warming trends. Large-scale circulation patterns shift naturally. Similarly, ocean circulation varies due to internal dynamics as well as external forcing. So while climate change can influence these systems, it is not responsible for every fluctuation. This is why scientists are careful not to overstate the connection. Current research suggests that climate change may contribute to Earth's rotation variability, but it is unlikely to be the dominant cause of the recent speeding up. Instead, it appears to be one influence among several, layered on top of core dynamics, natural atmospheric variability, and oceanic processes. Another factor to consider is groundwater. Human activity has redistributed large amounts of water by pumping groundwater from aquifers. That water eventually makes its way to the oceans. This shifts mass from continents to lower latitudes. Studies have shown that groundwater depletion has had a measurable effect on Earth's rotation, but again, the effect tends to slow rotation rather than speed it. Reservoirs built behind dams also redistribute mass. Water is stored inland, often at higher latitudes or elevations. This changes mass distribution. These human-driven effects are detectable, but small. What becomes clear is that climate change influences Earth's rotation indirectly, through mass redistribution, but the direction and magnitude of that influence depend on the specific processes involved. Some climate-driven changes push towards slowing, others can push towards speeding up, at least temporarily. The recent record short days likely reflect a moment where several accelerating influences aligned, including atmospheric and oceanic patterns that may themselves have been influenced by climate trends. But that does not mean climate change is causing Earth to spin faster in a simple linear way. It is not like turning up a dial. It is more like adding weight to one side of a spinning system while removing it from another, all while the system itself is already in motion and responding to other forces. There is also the matter of timescale. Climate change operates over decades to centuries. Core dynamics operate over years to decades. Tidal braking operates over millions of years. The recent acceleration has been observed over a few years. That alignment suggests that short-term processes, particularly atmospheric and possibly core-related, are the primary drivers of the current pattern. Climate change may modulate those processes, but it is unlikely to be the root cause. Another reason scientists are cautious is that similar accelerations likely occurred in the past, long before industrial climate change. As we discussed previously, length of day records show oscillations and variability that predate modern warming. That historical context matters. If Earth has sped up slightly before under natural conditions, then the current speeding up does not require a new explanation. Still, climate change introduces new boundary conditions. As ice continues to melt, as oceans warm, as atmospheric circulation shifts, the background state of the system changes. That can alter the amplitude or timing of natural oscillations. In other words, climate change may not create new rotational behaviour, but it can influence how existing processes express themselves. This makes the relationship subtle rather than dramatic. One way to think about it is this. Earth's rotation is like a complex instrument with many strings. Some strings are long and slow, like the moon's tidal influence. Some are shorter and faster, like winds and currents. Climate change slightly retunes some of those strings. The melody does not change entirely, but the harmonics shift. This perspective helps avoid both exaggeration and dismissal. Climate change does not threaten to destabilize Earth's rotation. It does not risk runaway acceleration or deceleration. The forces involved are far too small compared to the planet's overall angular momentum. But climate change does matter for precision timekeeping, because it alters the systems that exchange angular momentum with the solid Earth. As our measurements become more precise, these subtle influences become more visible. This brings us back to an important theme. Earth's rotation is not controlled by one process. It is the result of many systems interacting, each obeying the same physical laws. Climate change is now one of those interacting systems. Its influence is not dominant, but it is not negligible either. As long as we measure Earth's rotation with atomic precision, we will continue to see the fingerprints of atmospheric shifts, ocean circulation changes, ice melt, and crustal adjustment. The recent speeding up is best understood as a moment where several of these influences happen to align. Over time, that alignment will likely change. Atmospheric patterns will shift again. Ocean circulation will adjust. Core dynamics will evolve. The balance will move. If the recent acceleration is not permanent, and if Earth's rotation fluctuates naturally, how long might this current phase last? And what signs would indicate a return to slower rotation? There is a particular kind of uncertainty that appears only when measurements become extremely precise. It is not the uncertainty of ignorance, but the uncertainty of resolution. When you suddenly see details that were always there but never visible before, it becomes difficult to tell whether you're witnessing something new or simply noticing something old for the first time. That is exactly the situation we're in when we ask whether Earth's recent speeding up is temporary or the beginning of a new pattern. At a human scale, Earth feels dependable. Days follow nights, seasons cycle. Nothing about the planet's motion feels unstable or unpredictable. But at the level of milliseconds, Earth is not a metronome. It is a complex responsive system whose rotation speeds subtly adjust to internal and external changes. So when scientists see a cluster of unusually short days, the immediate question is not panic, it is context. What does temporary mean for a planet? And what would qualify as a new pattern when the system itself operates across timescales ranging from days to billions of years? To begin answering that, we need to look at how Earth's rotation behaves over time when examined carefully. Modern measurements show that the length of a day varies constantly. There is no perfectly smooth curve. Instead, there is a baseline trend, the long-term slowing caused by tidal friction with the moon, and layered on top of that are fluctuations of different sizes and durations. Some fluctuations last hours or days, driven by weather systems. Others last months or years, driven by atmospheric circulation and ocean dynamics. Some appear to last decades, potentially linked to interactions between Earth's core and mantle. The recent speeding up belongs to this layered variability. When researchers plot length-of-day data over the past century, they do not see a straight line. They see a wavy line gently trending upward overall, but with rises and dips along the way. In some periods, Earth rotates slightly faster than average, in others, slightly slower. What makes the recent period stand out is not that Earth is rotating faster than it ever has in absolute terms. It is rotating faster relative to the recent past, and faster than expected based on the long-term slowing trend alone. This distinction matters. If Earth had suddenly begun accelerating at a rate that overwhelmed tidal breaking over long time scales, that would be extraordinary. But that is not what the data show. Instead, the acceleration is modest and fits within the range of known variability. That strongly suggests a temporary phase rather than a permanent shift. Still, the clustering of the shortest days raises a legitimate question. Why now? Why do these records appear close together rather than spread evenly across decades? One possible explanation lies in oscillatory behaviour. Several studies have suggested that Earth's rotation exhibits quasi-periodic oscillations on timescales of several decades. These oscillations are not perfectly regular like a clock, but they recur often enough to be statistically meaningful. One commonly discussed oscillation has a period of roughly 60 years. Its origin is not fully understood, but it's thought to involve interactions between Earth's core and mantle, possibly combined with long-term climate variability. If such an oscillation exists, then periods of relative acceleration and deceleration would alternate naturally. The recent speeding up could represent the accelerating phase of such a cycle. In that case, the pattern would not be new at all. It would simply be one crest in a repeating wave. Supporting this idea, historical records suggest that similar deviations occurred in the mid-20th century, though measurement precision at the time was lower. When modern data are adjusted and compared with older astronomical observations, hints of past accelerations appear. They were simply harder to resolve. Another reason the recent acceleration may feel more significant than it is comes down to measurement density. We now measure Earth's rotation continuously, with daily resolution and extreme precision. Earlier generations relied on sporadic astronomical observations and long-term averages. Short-lived fluctuations would have been smoothed out or missed entirely. In other words, the present moment benefits from a microscope that did not exist before. This creates a subtle cognitive trap. When you first see fine structure in a system, it can feel like something has changed, when in reality, your ability to observe has changed. That does not mean the acceleration is illusory, it is real, but its apparent prominence may be amplified by our observational capabilities. There is also the issue of overlapping influences. Earth's rotation speed at any given moment reflects the sum of many effects acting simultaneously. Atmospheric angular momentum, ocean circulation, hydrological changes, core mantle interactions, seismic events, and post-glacial rebound all contribute to small signals. Most of the time, these signals partially cancel each other out. Occasionally they align. When several accelerating influences coincide, the result can be a noticeable dip in day length. This alignment does not need to persist indefinitely to produce record values. It only needs to persist long enough for a few particularly short days to occur. That appears to be what has happened recently. The atmosphere, for example, has spent several years in a configuration that reduces atmospheric angular momentum relative to the solid Earth. Ocean circulation patterns have also contributed in ways that favour slight acceleration. Core dynamics may be in a phase that transfers angular momentum outward. None of these factors alone would be remarkable. Together, they are enough to set records. The key question is whether this alignment is likely to persist. Based on what we know about each contributing system, persistence is unlikely. Atmospheric circulation patterns change, ocean currents adjust, core mantle interactions oscillate. Post-glacial rebound continues, but at a gradually declining rate. Seismic activity is episodic. There is no known mechanism that would lock all these systems into a permanently accelerating configuration. Tidal braking, meanwhile, does not turn off. The moon continues to pull. Energy continues to be dissipated. Over sufficiently long timescales that braking always wins. This means that even if Earth were to experience a few decades of net acceleration relative to recent history, the long-term trend would remain one of slowing. A truly new pattern would require a sustained reversal of that long-term trend. That would imply either a dramatic change in Earth-Moon dynamics or the introduction of a new external torque. There is no evidence for either. So from a physical standpoint, the idea of a permanent acceleration does not fit with known mechanisms. That brings us back to the word temporary. Temporary does not mean brief in human terms. It does not mean days or weeks. It can mean years or even decades. In planetary terms, decades are brief. So it is entirely plausible that Earth could continue to experience slightly shorter than average days for several more years, or even longer, without violating any physical principles. During that time, additional record-short days might occur. Discussions about negative leap seconds might intensify. Timekeeping organizations would monitor the situation carefully. Eventually, however, one or more contributing factors would shift. Atmospheric angular momentum might increase again. Ocean circulation might redistribute mass outward. Core dynamics might change phase. The balance would tilt back towards slower rotation. At that point, the length of the day would begin increasing again relative to atomic time, and the familiar pattern of leap seconds would resume. This interpretation aligns well with the historical record. Earth's rotation has always fluctuated around its long-term trend. The amplitude of those fluctuations varies, but the existence of variability is not new. What is new is our sensitivity to it. There is also a psychological dimension to this question. We are living in a time when change is often framed as unprecedented. Climate change, technological acceleration, social transformation, and environmental disruption all create a sense that familiar patterns are breaking. When Earth's rotation appears to change, it is easy to fold that observation into a broader narrative of instability. But physics demands caution. The systems governing Earth's rotation are well understood in principle, even if some details remain under investigation. The observed changes do not exceed expectations. They do not suggest a tipping point. They suggest responsiveness. Earth responds to changing conditions continuously. That responsiveness is not a flaw. It is a feature of a dynamic planet. Understanding whether the speeding is temporary or part of a new pattern also requires humility about prediction. Scientists are very good at explaining why something happened after it happened. Predicting exactly when rotation will speed up or slow down is harder because it depends on the alignment of multiple systems. What scientists can say with confidence is this: there is no evidence that Earth has entered a permanently accelerating state. There is strong evidence that Earth's rotation will continue to fluctuate around a long-term slowing trend. There is moderate evidence that current acceleration fits within known oscillatory behavior. There is high confidence that tidal braking will continue to dominate over geological timescales. Taken together, these points strongly favour the interpretation that the recent speeding up is temporary in the planetary sense, even if it persists for a while longer. This perspective also reframes the significance of the moment. The importance of the recent acceleration lies not in what it will do to the planet, but in what it reveals about the planet. It reveals how tightly coupled Earth's systems are. It reveals how small shifts in winds, water, and molten metal can influence something as global as rotation. It reveals the power of precise measurement to uncover subtle dynamics. In that sense, whether the speeding lasts 5 years or 15 is less important than the fact that we can see it at all. If Earth's rotation is this sensitive, if time itself depends on the balance of so many moving parts, what does that say about our place on this planet? How should we think about time, stability, and motion, when even the length of a day is not quite as fixed as it feels? Somewhere between one breath and the next, between one blink and another, the Earth turns. It does not announce itself. It does not pause to check whether we are paying attention. It simply keeps moving, carrying oceans, air, continents, cities, and every quiet sleeping room along with it. And that, perhaps, is the most grounding thought of all. Throughout this exploration, we have followed a question that sounds technical on the surface, but turns out to be deeply human underneath. Why is Earth's rotation speeding up? What does it mean when the day becomes shorter, even by an amount so small it can only be seen by atomic clocks and distant stars? The answer, as we've seen, is not a single cause or a dramatic event. It is not a crisis or a mystery that threatens stability. It is a story of balance, of mass shifting, of momentum being shared, of a planet that is not rigid or frozen in place, but responsive, layered, and alive with motion. The Earth spins because it always has. It spins because it formed that way, because angular momentum carried through its birth and never vanished. Over billions of years, the Moon has gently slowed that spin, stretching days longer, almost imperceptibly, almost patiently. At the same time, everything within the planet has continued to move. The core flows, the mantle creeps, the crust rebounds, the oceans circulate, the atmosphere breathes. Each movement is small on its own. Together they shape the rhythm of time itself. When the Earth spins slightly faster, it is not rebelling against the Moon or breaking a rule. It is responding to changes within its own body. Winds slow or shift, water moves, ice melts, rock adjusts, momentum redistributes, the equations balance, exactly as physics says they must. What makes this moment feel special is not the size of the change, but our awareness of it. For nearly all of human history, the length of a day was something felt, not measured. Dawn came, dusk followed. Time was read from the sky, from shadows, from routine. No one worried about milliseconds. No one needed to. Now, we live in an age where time is counted by atoms, where clocks drift by less than a second over millions of years, where satellites navigate by nanoseconds, where the difference between a stable network and a failed one can be smaller than a heartbeat. In that context, Earth's natural variability becomes visible, not because it has changed dramatically, but because we have. We have built tools sensitive enough to notice that the world does not turn with machine-like perfection, and rather than being unsettling, that realization can be quietly reassuring. It tells us that Earth is not a clock that is winding down or running away. It is a system in motion, continuously adjusting, continuously balancing forces that act across vastly different scales of time and space. The speeding up we observe now fits within that picture. It aligns with known physics. It matches patterns seen before. It is almost certainly temporary in the planetary sense, even if it persists for years. Eventually, atmospheric patterns will change. Ocean circulation will reorganize. Core dynamics will shift. The Moon's steady pull will continue. The balance will tilt again. And the day will lengthen once more by a whisper of a second. There is something humbling about realizing that time, the thing we schedule, divide, sell, and race against, is not perfectly uniform even at the scale of the planet itself. The day feels solid and dependable because it is close enough for life, close enough for habit, close enough for rest. Perfection is not required. The Earth does not need to spin at exactly the same rate every day to be stable. Life evolved under conditions where days were shorter, then longer, then shorter again. Coral grew, forests spread, animals adapted, humans appeared unaware of any of it. What matters is not constancy, but continuity. And continuity is exactly what Earth provides. The turning never stops. It does not rush. It does not hesitate. Even when the rotation speeds up by a millisecond, the planet remains calm. Gravity holds. The atmosphere stays bound. The oceans remain in place. Nothing shakes loose. The clocks may need adjusting. Our definitions may need refining. But the world itself is steady. In a way, leap seconds are a quiet metaphor for our relationship with nature. We adjust ourselves, not the planet. We insert a second. We skip one. We acknowledge that our systems sit on top of something older, larger, and not obligated to conform perfectly to our expectations. There is no drama in that, just alignment, and perhaps that is a comforting thought to carry into rest. While you lie still, the Earth continues to turn. Not hurried, not careless, just steady enough. The night moves across the surface. Somewhere, dawn is beginning. Somewhere else, dusk is fading. All of it unfolds without effort. Time passes, not as something you need to chase, but as something you are carried through. If the day is a fraction of a second shorter tonight than it was once, nothing is lost. Sleep still arrives, breath still slows, the world still holds together. The ticking you hear, if you hear one at all, is not the planet rushing. It is just the sound of our instruments trying to keep up. The turning world does not need to be perfect to be safe. It only needs to keep turning, and it does.